Every atom in your body was forged in a star that died before Earth existed, then scattered across space like cosmic ash. If the universe can assemble stardust into a mind that can wonder, imagine what it's building where our telescopes can't reach. Beyond the edge of what we can see, are there stranger laws, hidden worlds, or signs of life, waiting in the facts we're about to uncover? Look up, and you are not seeing the universe as it is, you are seeing the universe as it was. The night sky is a time machine with missing pages, and the gaps are where the stakes begin. Somewhere in that darkness, distance becomes a limit on knowledge, and the limit is not philosophical but physical. Light does not simply travel. It carries a timestamp, a fingerprint, and a history of the space it crossed. Every spectrum we split, every faint smudge we sharpen, is evidence filtered through motion, expansion, and noise. Yet the deeper we look, the more the universe insists on a strange rule. Much of what governs the cosmos cannot be seen directly. We infer it from how galaxies orbit, how clusters bend background light, and how patterns of matter repeat across unimaginable scales. This documentary is a guided descent through that measured strangeness. 30 mind-boggling space facts, each anchored in observation, each widening the question of what exists beyond our vision. We will begin with the horizon that defines what any telescope can ever confirm, and why the universe can be larger than its observable portion. We will follow ancient light back toward its earliest accessible glow, then confront the silent interval before stars existed. From there, the story becomes architectural. Filaments and voids, sprawling across hundreds of millions of light years, traced by galaxies like sparks on invisible wiring. We will see how an unseen mass shapes that structure, and why its identity remains one of physics' most stubborn open problems. Then the plot turns toward destiny, because the expansion of space is not merely continuing, it is accelerating, and the cause is still unnamed. We will explore how that acceleration rewrites what remains reachable, and how it frames every long-term future we can calculate. Next come the places where gravity becomes extreme enough to rearrange common sense. Black holes are not cosmic vacuum cleaners. They are precise predictions with observable consequences, and they test the boundaries of time, causality, and collapse. And we will learn to listen as well as look, because the universe has begun speaking in gravitational waves, carrying news of collisions that light may never report. These signals are not science fiction. They are measurements so delicate that they force technology to meet the scale of space-time itself. Beyond that, we approach the earliest chapter that photons cannot show us, where inflation and quantum seeds are proposed to explain the smoothness and structure we observe. We will keep our footing on evidence while acknowledging how quickly cosmology reaches the edge of what can be tested. But this is not a journey that ends in abstraction. We return to the engines that manufacture complexity, to the nuclear bookkeeping inside stars, and to the explosions and mergers that scatter the periodic table across galaxies. Then we move outward again, toward other worlds, strange climates, and atmospheric clues that might hint at biology without promising it. Throughout, one question tightens its grip. If the universe follows knowable laws, why does it contain so much that hides, and so many possibilities that remain unconfirmed? In the final facts, we confront the silence of the sky, the logic of the Fermi paradox, and the next measurements that could change the conversation. This is the awe of scale, disciplined by data. The universe may be stranger than our instincts allow, but it is not beyond understanding, and the evidence is already arriving, one photon and one ripple at a time. Tonight, we begin reading it. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. From the cosmic horizon to first light, from dark scaffolding to runaway expansion, each chapter adds a new constraint and a new wonder. Stay with us as the facts build into a single, testable story about origin, structure, and the search for life. Every atom in your body was forged in ancient stars, then scattered, recycled, and assembled into you. In stellar cores, lighter nuclei fused into heavier ones, and in supernova shockwaves, rare elements were stamped into existence. If physics can build a human from stardust, it can build other stories too. Some of those stories may be unfolding beyond the farthest light we can ever receive. Chapter 1 begins with a limit that shapes every cosmic question we ask. We call it the Observable Universe, and the name hides a warning. What we can observe is not identical to what exists. Observation is not the same as existence, and visibility is not the same as truth. The universe does not end where our sight ends, but our evidence often does. Even our best instruments translate faint photons into data, and that translation carries noise, bias, and uncertainty. The central question of this documentary starts here. What exists beyond what we can see, and how can we know anything about it? Fact 1 begins with a simple rule. Light has a finite speed, and nothing carries information faster. In vacuum, that speed is about 300,000 kilometers per second, and it sets the pace of every cosmic message. When you look outward, you look back in time, because the light left earlier. Telescopes are time machines, not by magic, but by delay. Each photon is a timestamp that finally arrives. Imagine the camera pulling away from Earth at night, city lights shrinking into a blue-white marble. The moon is about 1.3 light seconds away, so you see it as it was moments ago. The sun is about 8 light minutes away, so sunlight is already old when it warms your skin. If the sun vanished this instant, the sky would stay bright for 8 more minutes, because information cannot outrun light. Jupiter is tens of light minutes away, and its storms are always slightly in the past. Even in the solar system, the present is never perfectly shared. Beyond the planets, the delays become history, and the visuals change from familiar worlds to a crowded starfield. The nearest stars are years away, so their light began travelling before today's headlines and before this sentence began. The Milky Way's far side is tens of thousands of years away, so its glow predates agriculture and the first permanent cities. When we map our galaxy, we stitch together different eras into one picture, because each direction has its own built-in delay. Astronomy is a mosaic made of time, assembled from light that left at different moments. Andromeda is about 2.5 million light-years away, so we see it as it was before humans existed. The light entering a telescope tonight began its trip when early ancestors were just learning to walk upright on African plains. In a slow pan across Andromeda's spiral arms, the bright knots are star-forming regions, and the dark lanes are dust that blocks starlight. The farther we look, the more the universe turns into an archive, and the more that archive resembles a family album of cosmic adolescence. Distance becomes a timeline. Modern observatories push that timeline toward the beginning, and the images become both beautiful and strange. Deep surveys reveal galaxies so distant that their light left when the universe was young, long before the sun formed. Those early galaxies look smaller, clumpier, and more chaotic than today's giants, because they were still assembling through mergers and rapid star formation. Their colours shift toward red, not because they were born red, but because expansion stretches their light on the way to us. Their shapes record an era when gravity was still organising matter, and when gas had not yet settled into the calm disks we recognise. Look-back time is not a metaphor, it is a measurement. We can calculate when a photon was emitted and how long it travelled, using redshift as a kind of cosmic clock. We can compare nearby mature galaxies to distant youthful ones, and we can track how stars enrich their surroundings with heavier elements. In that comparison, we read a story of growth, collisions, and chemical enrichment, because spectra reveal fingerprints of hydrogen, helium, oxygen, and iron. The universe keeps its receipts in the spectrum of light, and those receipts are written in precise wavelengths. This time machine idea sets up a deeper constraint. If light takes time, then there is a maximum distance from which light could have reached us at all. That maximum is not fixed by our technology, but by the age of the cosmos and the way space has expanded. Even a perfect telescope cannot see what has had no time to send us a signal, because there is no earlier light to collect. The first boundary is simply time, and it is enforced by causality itself. Fact 2 names the boundary created by time and expansion. The observable universe is the region from which light has had time to arrive since the beginning, given the universe's changing expansion rate. The entire universe is whatever exists beyond that region, whether finite or infinite, and whether it resembles our neighbourhood or not. Observable is a statement about our past light cone, not a claim about total reality. The horizon is not a wall, it is a limit on information, an edge drawn by physics, not by matter. Expansion makes the horizon more subtle, and the visuals should shift to a grid of space stretching like fabric. space itself stretches, and that stretching changes what can reach us, because the distance a photon must cross grows while it travels. Some regions are so far away that their light is still en route and may never arrive, even given unlimited time. The cosmos can create distance faster than light can cross it, because the rule limits motion through space, not the growth of space. The horizon is a consequence of geometry, and geometry decides which events can ever influence us. This is why the observable universe is not the whole universe. There can be galaxies beyond our horizon that are as real as any we can see, with stars burning and planets forming in complete darkness to us. Their light may be redshifted, diluted, and carried away by expansion, sliding into wavelengths our eyes cannot detect. Their future signals may never overcome the increasing gap, because the space between us continues to stretch. Reality can extend beyond evidence, and the universe does not ask permission to exist. Fact 3 gives the number that surprises almost everyone. The universe is about 13.8 billion years old, yet the observable universe has a radius of about 46 billion light-years. The mismatch is not an error, and it does not mean anything moved faster than light through space. It means space expanded while the light was travelling, so the present-day distance to the source is larger than the light travel time suggests. The path length grew as the photon crossed it, like a moving walkway that lengthens while you walk. A useful distinction keeps the idea clear. Objects can be nearly at rest in their local space, yet become separated as space stretches between them. In that sense, recession is not ordinary motion, it is the metric changing, and the metric is the ruler we use to define distance. Distant galaxies can recede faster than light without violating relativity, because relativity constrains local speeds measured in a local frame. The horizon is built into the rules, and the rules are written into spacetime itself. So when we say a galaxy is 46 billion light-years away in today's distance, we are not saying its light travelled 46 billion years. We are comparing its current separation to a ruler that expands with the universe, a ruler defined by cosmological models and measured by redshift. The light travelled for 13.8 billion years, but the destination moved away during the trip and the space in between kept stretching. Cosmic distances require cosmic bookkeeping, and that bookkeeping depends on how expansion changed over time. This number also reframes the idea of an edge. The horizon is not the boundary of matter, but the boundary of what can have affected us, even in principle. It is the farthest region whose light has had time to reach Earth, after surviving absorption, scattering, and the dimming of distance. Beyond it, events may be happening right now, but they are not part of our observable story. The universe can be larger than its visible chapter, and the unseen pages may be the majority. Fact 4 turns the horizon into a census, and the visuals become a slow zoom into a deep field image. Deep field images show that what looks like empty darkness is packed with faint galaxies, each one a distant island of gravity and light. Each tiny smudge is a system of stars, gas, dust, and planets, often billions of suns arranged in spirals, ellipses, and irregular shards. Some of those photons began their journey before Earth existed, and they arrive as a whisper at the detector. By counting galaxies in small patches and scaling up, astronomers estimate the total in the observable universe. The result is staggering. Depending on definitions and faint-end corrections, the observable universe likely contains hundreds of billions to trillions of galaxies. Many are too dim or too redshifted to detect directly with current instruments because their light has been stretched into infrared and beyond. Some estimates rose when better surveys revealed more small and early galaxies, which are easy to miss in shallow observations. The inventory changes as our sensitivity improves, but the scale remains immense. Even conservative counts imply more worlds than imagination can comfortably hold, and more potential histories than any library could store. This abundance matters for more than awe. Galaxies are the factories where stars form and elements accumulate, and those elements become the chemistry of rocks, oceans, and cells. More galaxies mean more chances for long-lived stars, stable planets, and complex chemistry, even if life is rare in any one place. Yet the horizon also limits the search, because most galaxies are forever beyond reach, and even their radio whispers may never arrive. The universe may be teeming, and we may be confined to a small sample, like listening to one room in a vast building. Here the narrative tension sharpens. If we can only see a fraction of what exists, how do we infer the unseen with confidence, rather than with wishful thinking? Cosmology becomes a science of indirect evidence, where patterns in the visible region hint at the whole, and where consistency across many tests matters. We test models against the distribution of galaxies, the expansion rate, and the relic light from early times, because each dataset constrains the same underlying geometry. We use physics as a bridge across the horizon, but the bridge has assumptions about uniformity, about gravity, and about how matter behaved long ago. The horizon forces humility, but it also forces creativity, and it rewards careful measurement. We cannot travel to the edge, yet we can measure how the edge behaves, by tracking how distances and redshifts relate across the sky. We can map how structures cluster, and how light is stretched by expansion, and we can watch gravity bend light into arcs and subtle distortions. We can ask whether the universe is flat, curved, finite, or infinite using observable clues, because geometry leaves signatures in large-scale patterns. The unseen is not automatically unknowable, but it is never directly confirmed. There is also history in how we learn to speak about horizons. A century ago, astronomers debated whether spiral nebulae were nearby clouds or distant galaxies, until measurements settled the scale. Later, the discovery that galaxies are receding reframed the cosmos as dynamic, and the idea of a horizon became unavoidable. Each improvement in detectors and telescopes widened our view, yet each widening also clarified the limit we cannot cross. Progress did not erase the horizon. It drew it more sharply. The most important answers might lie beyond the horizon. The universe could be far larger than the observable sphere, perhaps unimaginably larger, with more volume outside our view than inside it. It could contain regions with different histories, different densities, or different outcomes of cosmic evolution, even if the same physical laws apply. It could even contain domains where the laws appear the same, yet the initial conditions differ, producing different cosmic architectures. Our horizon may be one bubble of information in a much bigger sea, and the sea may not be quiet. This is why every mind-boggling fact in this documentary is more than trivia. Each one is a clue about origin, structure, and the possibility of life, and each clue is constrained by what light can carry. The speed of light turns the sky into a timeline, where distance is a record of earlier states. Expansion turns that timeline into a boundary, where some chapters can never be delivered to us. The galaxy count turns the boundary into a scale of opportunity and isolation, because the sample is vast yet incomplete. Together they define what questions we can ask and what answers we can test. The opening hook returns with sharper edges. You're made of atoms forged in stars that died long before Earth existed, and those atoms travelled through cold interstellar space before joining a planet. Those atoms prove the universe can build complexity from simple beginnings, using only a few forces and a long stretch of time. If that process happened here, it likely happened elsewhere in the observable cosmos, in systems we can photograph as faint points. If it happened elsewhere, it may also be happening beyond the horizon, where we cannot yet listen, and where no future telescope may ever hear. Still, the horizon is not the beginning. It is a consequence of the beginning, and it inherits the universe's earliest conditions. To understand why the observable universe has the size it does, we must understand the early conditions that set expansion in motion, and how that expansion changed with time. We must ask what the universe looked like when it was young and hot, before galaxies and stars, when matter and radiation were tightly coupled. We must follow the light back toward its first possible sources until the cosmos becomes opaque and the trail ends. Transition. To understand the cosmic horizon, we must understand the beginning, when the universe was smaller, hotter, and filled with primordial light. Chapter 2 starts with the horizon story points. We follow the light backward until the universe itself blocks our view. The camera drifts past familiar constellations and into deep time, where distance becomes a kind of memory. Each fainter galaxy is not just farther away, it is also earlier, closer to the beginning. Fact 5 corrects the most common picture of the Big Bang. It was not a bomb detonating at one location in empty space. That popular image sneaks in a hidden assumption that space existed first, waiting like a dark room for an explosion. Modern cosmology replaces that intuition with a stranger claim. Space itself participates, and its expansion is part of the story. The Big Bang model describes an early state that was hotter, denser, and expanding everywhere at once. Space was not a stage. Space was part of the event. In general relativity, expansion is not a wind pushing galaxies outward through a static arena. It is the metric, the ruler used to measure distance, changing with time, so the same 2 points can be farther apart without either moving locally. A better analogy is rising bread dough with raisins. The dough expands, and every raisin sees every other raisin recede, even though no raisin sits at the center. If you zoom in on one raisin, it still looks ordinary and still obeys ordinary physics. That is the crucial point. Expansion is most visible on large scales, while local structures can remain bound and stable. Another analogy is a stretching grid drawn on rubber. Distances grow because the grid grows, not because objects race through the grid. On screen, the grid lines widen smoothly, and the dots barely slide across their squares. The motion is in the background geometry, which is why cosmologists speak of the expansion of space, rather than a spray of debris. This matters because it changes what we mean by beginning. The question is not where the universe exploded. The question is how the universe evolved from an extreme early condition. When we ask what happened, we are really asking about temperature, density, and the behavior of fundamental fields. We are also asking about time itself, because the earliest moments are not a place we can point to, but a state we can infer. In the first moments, the universe was a plasma of particles and radiation. Photons scattered constantly off free electrons and light could not travel far. This was a thermal bath where energy and matter traded identities with ease. High-energy photons could create particle, antiparticle pairs, and those pairs could annihilate back into photons, keeping everything tightly coupled. At that stage, the universe was opaque like the interior of a star. You could not see through it, because every direction was a fog of charged particles. Visually, it is not black space with bright points, but a glowing, uniform furnace. Any photon that tries to escape is immediately redirected, as if the universe were a dense cloud lit from within. Expansion cooled everything, and cooling changed the rules. When the temperature fell enough, electrons could finally bind to nuclei and make neutral atoms. Cooling here is not like a hot object losing heat into a colder room. The universe cools because expansion stretches wavelengths, draining energy from radiation, and because the same energy is spread through a larger volume. Fact 6 introduces the cosmic microwave background. The CMB is the afterglow of that transition, now cooled to about 2.7 Kelvin. That number is deceptively small, only a few degrees above absolute zero, yet it is the chilled remnant of a time when the cosmos glowed like a white-hot surface, and when the average photon carried thousands of times more energy. The key event is recombination, about 380,000 years after the Big Bang. Protons and electrons combined into hydrogen, and fewer free charges remain to scatter light. The word recombination is a historical quirk. There was no earlier combination in the Big Bang itself. It means that for the first time, stable neutral atoms could form and persist, because the ambient radiation had weakened enough. As the plasma turned into mostly neutral gas, the universe became transparent. Photons stopped bouncing around and began traveling freely across expanding space. This is sometimes called photon decoupling, because light and matter stop acting like a single fluid. The universe does not suddenly become empty. It becomes clear, as if fog has lifted from an endless landscape. Those photons are still arriving today, stretched by expansion into microwaves. They form a nearly uniform glow that fills the sky in every direction. If our eyes could see microwaves, the entire sky would shine with a soft, almost perfectly even light. It would not rise in the east or set in the west. It would be a sphere of illumination centered on every observer. The CMB is not light from stars, and it is not a later echo. It is the oldest light we can directly observe, a snapshot of the universe when it first cleared. When we look at it, we are looking at a surface in time, sometimes called the last scattering surface. It is not a physical wall, but a boundary beyond which the early universe is hidden behind its own opacity. Its spectrum is almost a perfect blackbody, which is a powerful clue. It tells us the early universe was once in thermal equilibrium, hot enough to erase earlier irregularities. A blackbody spectrum is the fingerprint of matter and radiation, exchanging energy so frequently that they forget their detailed histories. It is simple, smooth, and mathematically precise, so precise that small deviations become profound clues rather than noise. The discovery of the CMB in 1965 turned a debate into a measurement. It supported an evolving universe and ruled out many steady-state alternatives. Arno Penzias and Robert Wilson found it as an unexplained hiss in a radio antenna, a persistent background that would not go away. Nearby, theorists had predicted an afterglow from a hot early universe, and the pieces suddenly locked together. Uniform does not mean featureless, and the suspense lives in the details. When we map the CMB precisely, we find tiny temperature ripples across the sky. At first glance, the full sky map looks like static, a mottled pattern of reds and blues. Then the scale sinks in. Those colours represent temperature differences of mere millionths of a degree. Fact 7 is that these fluctuations are the seeds of all later structure. The variations are only tens to hundreds of microkelvin on top of 2.7 Kelvin. That contrast is like detecting a whisper in a stadium, yet it is measured with exquisite care. Satellites such as COBE, WMAP and Planck refined the map from a blur into a precise cosmic blueprint. Those ripples represent slight differences in density and gravitational potential. Where matter was a little denser, gravity pulled harder, and growth began earlier. In denser regions, photons also had a slightly harder time climbing out of gravitational wells, which subtly shifts the observed temperature. The CMB therefore encodes both the distribution of matter and the curvature of space-time at that early epoch. Where matter was a little thinner, expansion won more easily, and growth lagged. Over billions of years, that small head start became galaxies, clusters, and the cosmic web. It is a compounding process, like interest accumulating from a tiny initial deposit. Gravity amplifies differences, turning faint statistical wrinkles into the vast architecture that telescopes now trace across the sky. This is the bridge from early simplicity to later complexity. A nearly smooth universe still contained the blueprint for everything that would later shine. The remarkable part is not that structure exists, but that it is intelligible. The same physical laws that govern falling apples also govern the slow collapse of gas into galaxies, across scales that dwarf imagination. The CMB also carries a pattern of acoustic peaks. These are imprints of pressure waves in the early plasma, frozen at the moment the universe became transparent. Before recombination, matter and light behaved like a coupled fluid, and gravity tried to compress it while radiation pressure pushed back. The result was a set of standing sound waves, cosmic acoustics written across the sky. Those peaks let cosmologists measure basic parameters. They constrain the universe's geometry, the amount of ordinary matter, and the overall mixture of components. The spacing of the peaks reveals whether space is flat or curved on large scales, and the relative heights reveal how much baryonic matter was available to deepen compressions. It is a kind of cosmic spectroscopy, but for the universe's earliest vibrations. Yet the CMB also exposes a problem that will grow larger in later chapters. The ripples we see cannot grow fast enough into today's structures using only ordinary matter. Ordinary matter interacts with radiation, which slows its collapse in the early universe. If atoms were the only gravitating ingredient, the universe would struggle to build galaxies quickly enough to match what we observe. That tension points to invisible mass that does not interact with light. It is one of the first places the universe hints that most of its matter is not the kind we know. The hint is indirect, but persistent, like footprints that appear in fresh snow while the walker remains unseen. We do not see the dark component in the CMB as light, but we see its gravitational influence in the pattern. Before we follow that mystery, we stay with the first chemistry. The early universe did not start with the periodic table we learn in school. In the beginning, there were no rocks, no oceans, and no carbon chains. There were only the simplest nuclei, and a radiation field so intense that complex atoms could not survive. Fact 8 is that most ordinary matter is hydrogen and helium made in the first minutes. This is Big Bang nucleosynthesis, when the universe was hot enough for fusion. This era begins seconds after the start, when temperatures fall enough for protons and neutrons to exist as distinct particles rather than a seething soup. It ends minutes later, when expansion cools the universe below the threshold for efficient nuclear reactions. In roughly the first 3 minutes, protons and neutrons combined into light nuclei. The main products were hydrogen, helium-4, and a trace of deuterium and helium-3. The ratio of protons to neutrons mattered enormously, because neutrons are slightly heavier and can decay. As the universe cooled, fewer neutrons survived, and the ones that did were quickly locked into helium-4, the most stable light nucleus. A tiny amount of lithium formed as well, though the exact abundance has long been a puzzle. The overall outcome is robust because it depends on well-tested nuclear physics. When astronomers measure primordial deuterium in ancient gas clouds, they are effectively reading a fossil record of those first minutes. Deuterium is especially sensitive to conditions, so it acts like a thermometer and a clock for the early universe. The universe did not make heavy elements then, and the reason is simple. Expansion cooled the cosmos too quickly, and the density dropped before complex fusion chains could proceed. Fusion needs not only heat, but time and collisions, and the early universe raced ahead too fast. In that brief window, nuclei could form only along the easiest pathways, and then the reaction network froze out. There is also a bottleneck at mass 5 and mass 8. Without stable nuclei at those steps, building carbon and oxygen in the early universe is extremely inefficient. Nature left no stable stepping stones at those masses, so the assembly line stalled. To leap the gap requires rare multi-particle collisions, and the early universe became too dilute before those unlikely events could matter. So the early universe left the job unfinished on purpose, in a sense. It produced the fuel, then waited for stars to become the furnaces that could forge everything else. That waiting is visible in the sky's later chapters, when gravity gathers gas into the first stellar cores. Only inside stars do temperatures and pressures remain high long enough to build carbon, oxygen, silicon, and the iron group. This connects back to the opening hook of the documentary. Your carbon, oxygen, and iron were not made in the Big Bang. They were made later, inside stars and stellar explosions. On screen, the story shifts from a smooth early glow to the violent beauty of stellar deaths. Supernova shockwaves and expanding nebulae become the factories that seed future planets with the elements life requires. The Big Bang gave the universe its simplest ingredients. Stars turned those ingredients into chemistry, and chemistry eventually turned into biology on at least one world. That chain is not guaranteed, and it raises a quiet question. If the early universe had been even slightly different, would complex chemistry ever have had a chance to begin? The CMB and primordial element abundances agree with each other. Together they form a cross-check that the early universe was real, hot, and governed by the same physics we test on Earth. This agreement is one of science's most satisfying convergences because it links the larger scales to laboratory measurements. Nuclear reaction rates measured in accelerators help predict helium fractions, and the sky confirms them with astonishing consistency. Now we widen the frame to a deeper principle. The early universe was filled with charged particles, yet on large scales it is electrically neutral. That neutrality is not a trivial detail, because electromagnetism is vastly stronger than gravity at the particle level. If the cosmos carried even a small net charge, it would reshape everything we're about to describe. Fact 9 is that the universe is neutral overall, but still shaped by invisible forces. Gravity dominates cosmic structure, and electromagnetism shapes matter locally through plasma, fields, and radiation. Gravity is patient and cumulative, adding tiny attractions across immense distances until they become decisive. Electromagnetism is immediate and intricate, sculpting how gas cools, how stars ignite, and how light interacts with the matter we can detect. Neutrality matters because it prevents large-scale electric forces from overwhelming gravity. If the universe had a net charge, electric repulsion or attraction would drastically alter expansion and structure. In that alternate universe, galaxies might never form in the way we know, because electric forces would shove matter apart or lock it into different configurations. The fact that gravity gets to write the large-scale script is a precondition for the cosmic web. Even with neutrality, electromagnetic effects still matter for what we can see. Light couples to charged particles, and that coupling is why the early universe was opaque before recombination. The same coupling also powers the diagnostic tools of astronomy, because atoms and ions absorb and emit light at specific wavelengths. In a sense, electromagnetism is how the universe reports on itself, even when gravity is doing the heavy lifting. After recombination, photons largely decoupled from matter, and the universe entered a long dark age. Gas slowly fell into gravitational wells, and the first stars ignited much later. The visuals dim to near black, with only the faint microwave afterglow filling space. In that darkness, matter is not idle. It is gathering, cooling, and preparing for the first sparks that will eventually puncture the cosmic night. Here the narrative tension sharpens again. We can see the first light that escaped, yet we cannot see the dominant matter that shaped the wells. We can map the initial ripples with high precision, but we cannot point a telescope at the main ingredient that amplifies them. The universe is offering evidence without showing the culprit, and that is where the mystery gains force. The CMB tells us the universe began almost smooth, then grew complex. It also tells us ordinary atoms are only a small fraction of the total cosmic budget. Even without naming exact percentages here, the implication lands clearly. What we touch and breathe is not the main mass of the cosmos. The familiar world is a thin layer on top of a deeper gravitational framework. Measurements from the CMB, galaxies, and gravitational lensing converge on the same unsettling conclusion. Most matter is dark, and most of the energy driving expansion is darker still. Each method is a different line of evidence. Early universe sound waves, the motions of galaxies, and the bending of light by gravity. When independent approaches agree, the conclusion becomes difficult to dismiss as a mere artifact. We do not introduce those components as magic. We introduce them as names for consistent measurement results that ordinary matter cannot explain by itself. In science, a name is not the end of understanding, but a placeholder for a pattern. Dark matter and dark energy are labels attached to behaviors we can quantify, test, and challenge with better data. Dark matter acts like extra gravity that clumps and builds scaffolding. Dark energy acts like a pressure or field that changes the expansion rate on the larger scales. The language is careful because the physics is still being pinned down. What matters for this chapter is the role. One component helps structure form, and another shapes the universe's long-term expansion history. The early universe already hints at both. The CMB's pattern fits a universe where unseen mass helped structure grow, and where the later expansion history is not simple slowing. Even in the baby picture, the universe is already telling us that the visible ingredients are insufficient. The fit between theory and observation improves dramatically when an invisible gravitational component is included. This is why the CMB is more than a relic image. It is a map of initial conditions, and it is also a ledger of what the universe contains. It is a ledger written in temperature, polarization, and statistical patterns across the sky. By decoding those patterns, cosmologists infer densities, expansion rates, and the subtle interplay of matter and radiation. We return to the central question with new leverage. If most of reality is invisible to our eyes, then meaning and origins must be inferred from subtle, testable traces. That is the discipline and the wonder of cosmology, learning to trust faint signals, learning to separate foreground noise from primordial information, and learning to accept that the universe can be measured even when it cannot be held. The universe left us one of its earliest receipts in microwave light. It also left us a chemical signature in hydrogen and helium that still dominates cosmic matter. These two relics, radiation and composition, are independent witnesses that tell the same story. Together they say the early universe was hot, dense, and expanding, and that its physics was continuous with the physics we know. From tiny ripples and simple elements, everything else followed. Galaxies formed, stars ignited, planets cooled, and at least one planet learned to measure the sky. When that planet looks back, it does not see a single origin point. It sees a sky filled with evidence, an afterglow in microwaves, a chemistry in atoms, and a structure in galaxies that all began as almost nothing. Transition. The CMB is a map of early conditions. Now we follow those conditions forward into the cosmic web and the hidden scaffolding that built galaxies. Next chapter moves from the baby picture to the grown structure. We track how gravity amplified the ripples into filaments, voids, and clusters across billions of years. The CMB gave us a baby picture of the universe, almost smooth with tiny ripples. Now we follow those ripples forward into the grown-up architecture of galaxies. Those faint temperature variations were not just cosmetic noise on an ancient screen. They were density differences, slightly more matter here, slightly less there, seeded when the universe was young and still cooling. As the universe expanded, gravity began to act like a slow sculptor. Over billions of years, it pulled harder on the slightly denser regions, and it let the emptier regions fall further behind. On the larger scales, the universe is not a random spray of islands. It is patterned like a network, with dense knots connected by long bridges. When we visualize it, the scene feels less like scattered fireworks, and more like a three-dimensional spiderweb. Bright nodes flare where clusters sit, while faint strands stretch between them like luminous threads in deep space. Fact 10. Galaxies are strung along vast filaments, with enormous voids between them. This pattern is called the cosmic web, and it spans hundreds of millions of light years. The cosmic web is what you get when gravity amplifies early irregularities, but does so in an expanding universe. Matter collapses most efficiently along one direction, then two, and only later toward compact knots, so sheets and filaments appear naturally. In surveys, galaxies trace threads that intersect at clusters and superclusters. Between those threads, there are voids so empty that even dwarf galaxies are rare. A modern redshift survey turns this into a cinematic reveal. Points of light become a map, and the map becomes a structure. Walls, tendrils, and cavernous gaps that look carved rather than accidental. Those redshifts are not just distances, and they are not just colours. They are recession speeds imprinted by expansion, letting astronomers reconstruct a three-dimensional census across enormous volumes. A supercluster is not a single object with a clean edge. It is a region where clusters and filaments crowd together, shaped by shared gravity over immense distances. Historically, this realization arrived in stages. As telescopes and catalogues grew, early astronomers saw clusters, then noticed larger associations, and eventually recognized that large-scale structure was a genuine cosmic phenomenon. The scale is the first shock. A filament can be tens of millions of light-years long, and a void can be 100 million light-years across. To picture a void, imagine a sphere so wide that light needs 100 million years to cross it. Inside, there is still matter, but it is thin, more like a haze than a city. This structure is not decoration on top of the universe. It is the record of gravity amplifying early differences, turning microkelvin ripples into cosmic geography. In that sense, the web is an archive written in matter. The CMB shows the initial conditions, and the cosmic web shows what those conditions became after 13.8 billion years of gravitational evolution. Yet the visible galaxies are only the lit-up parts of the map. The web's main mass is not the stars we photograph, and that is where the tension rises. The starlight we love is a tracer, not the full substance. It is like foam on a wave, beautiful, informative, and real, yet not representative of the ocean's total mass. Fact 11. Dark matter outweighs ordinary matter by roughly 5 to 1. In the cosmic mass budget, atoms are the minority, even inside many galaxies. Ordinary matter means baryons, the protons and neutrons that build stars, planets, and people. Dark matter means mass that pulls by gravity, but does not shine. The phrase mass budget is a bookkeeping idea with profound consequences. When we total the universe's matter content, most of it does not participate in chemistry, and most of it never forms atoms. This ratio is not guessed from one experiment. It is inferred from multiple measurements that agree, including the CMB, galaxy clustering, and lensing maps. The CMB constrains the mixture because different ingredients leave different fingerprints. Baryons interact with radiation and change the heights of acoustic peaks, while dark matter adds gravity without adding light-scattering particles. Galaxy clustering adds a later time confirmation. The way galaxies clump across scales depends on the underlying matter distribution, and the observed pattern matches a universe dominated by non-baryonic mass. The implication is unsettling and clarifying. Most of the matter that shaped the Milky Way never became a star and never emitted light we can collect. If atoms are only a small fraction, then the familiar universe is a thin, luminous skin. Beneath it sits a deeper framework that sets the stage for formation. So what is dark matter, in operational terms? It is whatever provides extra gravitational pull without the electromagnetic signatures of ordinary gas and dust. That definition is deliberately practical, because it is built from what we can measure. We infer mass from motion and from lensing, and then we ask what kind of substance can fit all constraints at once. We do not define it by mystery. We define it by evidence that ordinary matter alone cannot reproduce, even when we count faint gas and hidden stars. Over decades, astronomers tried to close the gap with mundane explanations. They searched for dim stars, cold gas, and dusty reservoirs, but the numbers never add up across every environment. Fact 12. We infer dark matter from rotation curves, gravitational lensing, and galaxy cluster dynamics. Each method is a different way to weigh the invisible. Start with rotation curves, the simplest intuition. In a solar system, outer planets orbit slower because most mass sits near the center. Kepler's laws capture that logic in a clean mathematical form. If mass is concentrated, orbital speeds fall with distance, so the outer system moves more gently than the inner system. Galaxies do not behave that way. Stars far from the centre orbit too fast, as if extra mass surrounds the galaxy in a wide halo. The mismatch is not a small tweak at the edge. In many spirals, the rotation curve stays nearly flat for tens of thousands of light years, long after the bright starlight has faded. The picture is like a spinning record that should slow at the edge but does not. The speed stays high, implying a gravitational field stronger than starlight suggests. Visually, imagine tracing a glowing spiral with a speedometer. The needle refuses to drop, even as the galaxy's luminous disk thins into darkness. Astronomers measure these speeds through Doppler shifts in spectral lines. The data points do not drop as expected, and the discrepancy grows with radius. In practice, different tracers fill in different radii. Optical emission lines track ionized gas in the bright disk, while radio observations of neutral hydrogen extend the curve far into the faint outskirts. Could the missing mass be ordinary matter we fail to see? Dust blocks light, but dust also glows in infrared, and the accounting still comes up short. Even if you add every plausible baryonic component, stars, gas, dust, and compact remnants, the total remains too small. The gravitational pull required by the rotation curve demands a much larger halo. Could gravity itself be different on galactic scales? Modified gravity ideas exist, but they must also match lensing, clusters, and the early universe blueprint. That is the hard part. A successful theory must be universal. It must reproduce the same phenomena in dwarf galaxies, giant spirals, cluster collisions, and the CMB's precise pattern. Next, weigh galaxies using clusters. A cluster is a swarm of galaxies bound together, moving in a shared gravitational well. Clusters are among the universe's largest gravitationally bound structures. They contain hundreds or thousands of galaxies, and they sit at the intersections of filaments like beads where threads meet. If you measure the galaxy's speeds, you can estimate the cluster's total mass. The motions are too fast to be held by visible matter alone. This method has historical weight because it was noticed early. In the 1930s, Fritz Zwicky studied the Coma cluster and argued that unseen mass was required to keep it gravitationally bound. Hot gas in clusters adds more baryons than stars do. X-ray observations reveal enormous reservoirs, yet even gas plus stars still cannot supply enough gravity. In X-ray images, the intracluster medium glows like a vast fog heated to tens of millions of degrees. That heat comes from gravitational infall and shocks, and it reveals where baryons actually reside. Then comes the cleanest geometric test. Gravity bends spacetime, and bent spacetime bends the path of light. This is not a metaphor, and it is not a small correction. In general relativity, mass and energy curve the geometry itself, so light follows the straightest possible paths in a curved space. Fact 13. Gravitational lensing can magnify distant galaxies like a natural telescope. Mass acts like an optical element, not by refraction, but by curvature. When a massive object sits between us and a background galaxy, it can distort the background image. The result can be arcs, rings, or multiple images. In a strong lensing scene, the visuals are unmistakable. A distant galaxy becomes a stretched crescent, sometimes wrapping into an Einstein ring that looks like a halo of light around the foreground mass. That is strong lensing, where the distortions are dramatic and obvious. It usually requires a dense mass concentration, like a galaxy cluster. Strong lensing also gives precision constraints, because the geometry is tight. The positions and shapes of multiple images let astronomers reconstruct how mass must be distributed to produce the observed patterns. Weak lensing is subtler and more powerful statistically. Many background galaxies are stretched slightly, and the pattern reveals the foreground mass distribution. Individually, each galaxy's shape is messy, because galaxies are born irregular, yet across millions of them, a coherent shear emerges, tiny alignments that betray the presence of intervening mass. Weak lensing does not need perfect alignment. It needs large samples and careful correction for telescope effects. Then it yields a map of invisible mass. The analysis is painstaking because instruments leave their own fingerprints. Astronomers model the point spread function, calibrate distortions, and then separate the lensing signal from the noise of intrinsic galaxy shapes. The key point is that lensing measures gravity directly. It does not care whether the mass is bright, dark, hot, cold, or made of atoms. This is why lensing is so important to the central question. It lets us detect what exists beyond what we can see, using light as a probe of geometry. Lensing also turns the universe into a tool. A cluster can boost the brightness of a background galaxy, letting us study objects otherwise beyond reach. The lens can stretch and magnify, effectively increasing a telescope's resolving power. Nature provides an extra aperture, though it comes with distortions that must be modelled rather than ignored. In deep surveys, lensing reveals galaxies from very early times. Some of our best views of the young universe are borrowed through these gravitational windows. When we watch those magnified smudges, we are seeing light that began its journey when the universe was a fraction of its current age. The lens in the foreground becomes a bridge across time as well as space. So far, the evidence says there is extra mass and it clusters. Now we ask a sharper question. Does that mass behave like a new kind of particle? If dark matter were merely a bookkeeping trick, it would not have consistent behaviour across contexts. Instead, it appears to form halos, to seed filaments, and to act as a collisionless component in violent events. Fact 14 brings the story to a decisive collision. When galaxy clusters crash, different components respond differently, and the separation becomes measurable. A cluster collision is a slow catastrophe on a grand scale. Two enormous systems approach over billions of years, then pass through each other at thousands of kilometers per second. In a cluster, most ordinary matter is not in stars. It is in hot, thin gas between galaxies, glowing in X-rays and slowed by pressure during impact. That gas behaves like a fluid, even though it is extremely tenuous. When clusters collide, the gas clouds slam, shock, and heat further, leaving bright X-ray structures that mark where baryons have piled up. Galaxies themselves are mostly empty space, so they pass through each other with few direct collisions. Dark matter, if it interacts weakly, should also pass through. This is the crucial separation of behaviours. Stars and galaxies act like collisionless particles, while the gas acts like a breaking, compressible medium that cannot simply ghost through the encounter. In bullet cluster-style systems, we see exactly that separation. The hot gas lags behind like a wake, while the lensing mass peaks move ahead with the galaxies. Visually, the composite image is striking. Pink or blue X-ray emission pools in the middle, while lensing contours, often drawn as smooth-coloured hills, sit offset, centred on where the galaxies have continued onward. The mass map from lensing does not sit where the brightest baryonic mass sits. It sits where the collisionless components went, implying a dominant non-luminous mass. This is difficult to explain with ordinary matter alone. If the missing mass were just hidden gas, it would collide and slow with the visible gas. It is also difficult for many modified gravity models. They must reproduce a mass distribution offset from the baryonic plasma, while still matching lensing geometry. The collision evidence does not tell us what dark matter is made of. It tells us how it behaves, and that behaviour looks like a new, mostly collisionless component. That behavioural clue matters, because it narrows the possibilities. Whatever dark matter is, it cannot strongly scatter off itself like ordinary gas, and it cannot be tightly coupled to light or electromagnetic forces. Now the tension becomes personal and philosophical. The atoms forged in ancient stars built us, yet those atoms are not the main mass of our own galaxy. We live inside a halo we cannot see. Our solar system moves through an invisible sea, and our galaxy's spiral arms ride on a dark scaffold. If you could remove the stars and keep only the mass, the Milky Way would still be there as a gravitational object. Its halo would extend far beyond the visible disk, enclosing satellite galaxies and streams like a vast unseen envelope. This scaffold also explains the cosmic web. In simulations, dark matter collapses first into filaments and knots, and ordinary gas falls into those wells later. Those simulations start with the CMB's tiny fluctuations, and then let physics run forward. Under gravity, the overdense regions grow, merge, and form a hierarchy of halos, while the emptiest regions become the expanding voids. Because dark matter does not couple to light, it can begin clumping earlier. It is not held back by radiation pressure in the way ordinary matter was before recombination. Before recombination, baryons were tied to photons in a hot plasma, and pressure resisted collapse. Dark matter, by contrast, could start forming gravitational wells, preparing the terrain that baryons would later fall into. Over time, the dark web becomes the gravitational template. Gas streams along filaments, cools, forms stars, and lights up the structure we then observe. Cooling is not automatic, and it is not instantaneous. Gas must radiate energy away through atomic transitions, then fragment into denser clouds, and only then can star formation ignite in earnest. So the cosmic web is not built by galaxies. Galaxies are the glow that traces a deeper architecture, like city lights outlining roads at night. That analogy has a second layer. City lights show where people live, but the roads and power lines shape where cities can grow. Dark matter plays the role of infrastructure, guiding assembly long before the lights turn on. This framing changes how we think about origins. The universe did not start with galaxies, then add dark matter as an afterthought. It started with a mixture, and the invisible part did much of the early organizing. The visible part followed because gravity is democratic about what it pulls. What could dark matter be at the particle level? It is not ordinary atoms because atoms absorb and emit light, and we would detect that. It is not simply black holes in the required amount, because their formation history and lensing signatures are constrained. Some could exist, but not enough to dominate. Leading candidates are new particles that rarely interact with normal matter. They would be stable, abundant, and cold enough to clump into halos. Cold here is a technical term, meaning slow-moving compared with the speed of light when structure began to form. If the particles were too fast, they would wash out small-scale structure, leaving a smoother universe than we observe. WIMPs were once the most discussed option, motivated by theories beyond the standard model. Axions are another candidate, extremely light but able to behave like cold matter. WIMPs would be heavy particles that interact via the weak force or something similar, making them difficult but not impossible to detect. Axions, in contrast, would be produced abundantly and behave collectively, and experiments search for their subtle conversion into photons. There are also broader possibilities, including sterile neutrinos or hidden sector particles. The common requirement is gravitational influence with minimal electromagnetic coupling. Experiments on Earth search for rare collisions between dark matter and detectors. Telescopes search for annihilation or decay signals, and so far the silence is instructive. That silence is not empty information. Each non-detection redraws the map of viable particle properties, ruling out interaction strengths and masses that once seemed promising. The silence does not remove the evidence for mass. It narrows the space of possibilities, and it pushes us toward more careful models and more sensitive tests. This is the documentary's central question in action. We are measuring what exists beyond what we can see, and the measurements force new physics onto the table. The cosmic web becomes a kind of laboratory. Its filaments, voids, and cluster collisions constrain how dark matter moves, clumps, and possibly self-interacts. If dark matter were warm and fast, it would smear out small structures. If it were strongly self-interacting, halos would look different in lensing and dynamics. So the sky is not only a backdrop for wonder, it is a dataset that tests particle properties across scales no accelerator can reach. A particle collider can probe high energies for fleeting instants, but the universe runs a different experiment. It evolves for billions of years, and it reveals the cumulative results in the shapes of halos and the statistics of structure. We return to the opening hook with a new twist. Stardust built our bodies, but stardust is riding inside a darker ocean that shaped where stars could form. Meaning and origins now sit on two layers. There is the luminous story of atoms and fire, and there is the invisible story of gravity's hidden architecture. The chapter closes on a widening horizon of ignorance and method. We can map the dark scaffold, yet we still do not know its substance. That gap is not failure, it is a frontier. The universe is telling us that the standard model is incomplete, and it is telling us through gravity. As we refine surveys and lensing maps, we are not merely adding detail to a picture. We are tightening the rules that any dark matter candidate must obey, and we are learning which explanations can survive contact with the sky. Transition. Matter builds structure, but another component controls the universe's fate. The next chapter confronts an expansion that is not slowing down, but speeding up. Transition. Matter builds structure, but another component controls the universe's fate, and the next clue arrives from dying stars. For most of the 20th century, cosmologists expected gravity to slow expansion over time, because attraction accumulates as more matter falls within a growing horizon. The The question was how much slowing, not whether the trend could reverse, and that assumption shaped decades of calculations, debates, and telescope proposals. Edwin Hubble's discovery showed galaxies receding, and general relativity allowed an expanding metric, so expansion itself became a legitimate physical solution. Yet the default intuition still said attraction should gradually break the outward flow, like a ball thrown upward, still climbing, but losing speed. To test that breaking, astronomers needed a way to measure cosmic distances far beyond nearby galaxies, where parallax and ordinary standard candles fail. They needed a standard candle, bright enough to be seen across billions of light years, and reliable enough that small errors would not masquerade as new physics. Type Ia supernovae became that tool because they explode at nearly uniform peak brightness, and because their light curves can be standardized even further. A white dwarf approaches a critical mass, ignites runaway fusion, and detonates with repeatable power, briefly outshining an entire galaxy. Visually, the event is almost serene at first, one point of light swelling in a spiral arm. Then it becomes a beacon, a hard white flare that fades through weeks. Spectra reveal broad absorption lines from fast-moving debris, and the fingerprint of silicon helps identify the explosion as type Ia. The method is simple in principle and brutal in practice, because the universe does not hand us clean measurements. Measure the supernova's apparent brightness, compare to its intrinsic brightness, and infer distance from the dimming, while correcting for dust, colour and instrumental quirks. Then measure redshift from the host galaxy's spectrum, and connect distance to expansion history, because redshift encodes how much space stretched during the light's journey. The plot becomes a time machine that tracks how the scale of space changed, and it turns each dying star into a mile marker on a cosmic road. In the 1990s, this approach matured because detectors improved, surveys became systematic, and computers could fit light curves with consistent pipelines. Teams began targeting supernovae at redshifts around 0.5 and beyond, where the difference between deceleration and acceleration becomes measurable. Fact 15. In the late 1990s, two teams found distant type Ia supernovae were dimmer than expected. The universe was not merely expanding, it was accelerating. That result was shocking because acceleration implies a repulsive effect in the cosmic bookkeeping, not just a small correction to known matter. It suggested that something acts against gravity on the larger scales, pushing the metric outward in a way that grows more important as the universe thins. The teams checked dust, evolution, and selection bias because the claim was extreme and because astronomy is full of subtle confounders. Could grey dust be hiding light without reddening it much? Could early supernovae differ in composition? Could surveys preferentially find brighter events? The signal persisted across samples, calibrations, and independent analyses, and the tension refused to go away. Acceleration also fit other emerging measurements, including large-scale structure and the CMB's parameter constraints, which were becoming precise enough to cross-check the supernova story. Separate lines of evidence began pointing toward the same missing ingredient, as if multiple instruments were hearing the same low note beneath the cosmic symphony. In general relativity, expansion responds to energy density and pressure, not just mass, and that is the conceptual hinge most people miss. A component with sufficiently negative pressure can drive accelerated expansion because pressure contributes to gravity's source term in Einstein's field equations. That phrase sounds abstract, but it has a concrete meaning in Einstein's equations, where geometry and stress energy are locked together. Pressure gravitates, and negative pressure can produce an outward push in the metric, a kind of tension in space that resists being diluted. The name for this driver is dark energy, a label for a measured effect rather than a known substance, and the term is intentionally cautious. It is defined by what it does to expansion, not by what it is, and that distinction matters when the physics is still unsettled. And now, we arrive at the number that should genuinely unsettle you, a single statistic that quietly rewrites your place in the cosmos. Because if dark energy is real, and negative pressure is really pushing space apart, then almost everything you've ever seen, touched, or called the universe is a rounding error. Just how small a rounding error? The answer is one of the strangest facts in all of science, and later in this video we'll show you where this invisible majority is dragging the entire cosmos toward an ending almost nobody talks about. For now, look at the inventory itself. Fact 16. Dark energy makes up about 68% of the universe's total energy density. Ordinary atoms are only about 5%, and dark matter fills most of the rest. This reorders perspective on the opening hook about stardust and life, because the familiar is not the dominant. The atoms that built us are precious, but they are a thin layer in the cosmic inventory, like a bright foam riding atop a much deeper, darker ocean. The cosmic web from the previous chapter sits inside a much larger story of expansion, and the contrast is striking on screen. Dark matter shapes structure locally, while dark energy dominates the long-term dynamics, so the universe can be lumpy in detail yet smooth in its overall acceleration. To understand why, we need the Friedmann equations, the simple rules for an expanding universe, derived by applying general relativity to a homogeneous cosmos. They relate expansion rate to the densities of radiation, matter, curvature, and dark energy, and they show how different components dilute as space grows. Matter density thins as space grows, so its gravitational influence fades with time, because the same mass spreads through a larger volume. Dark energy, in the simplest model, does not dilute the same way, so its relative importance increases as the universe expands. So the universe has epochs, and each epoch leaves a different observational imprint. Radiation dominated early, matter dominated for billions of years, and now dark energy appears to be taking over, shifting the universe from structure building to acceleration-dominated evolution. The supernova result did not just add a new parameter, it changed the narrative of cosmic destiny. It forced a new question about what the far future can be, because acceleration alters horizons, isolation, and the ultimate accessibility of information. If expansion accelerates, distant galaxies will eventually recede beyond our horizon, not because they move through space, but because space grows between us. The observable universe becomes a shrinking island of accessible information, and the night sky slowly loses its farthest landmarks. That is a direct answer to the central question about what exists beyond what we can see, and it is a strangely bittersweet one. There can be more reality out there, yet it becomes permanently unreachable, not by technology, but by geometry and dynamics. The simplest explanation for dark energy is not new at all, and that historical twist is part of the drama. Einstein introduced a cosmological constant as a term that acts like energy built into empty space, and he later regretted it when expansion was discovered. In the equations, the cosmological constant is deceptively clean, and that cleanliness is seductive for theorists. It behaves the same everywhere and everywhen, so it naturally produces a smooth acceleration, and it does not clump into galaxies the way matter does. Fact 17. A cosmological constant behaves like vacuum energy, with constant density and negative pressure. It fits current data well, but theory predicts an absurdly larger value. This mismatch is called the vacuum catastrophe, and it is one of physics' worst disagreements, not a minor discrepancy. Quantum field theory says empty space contains fluctuating fields with enormous energy, and those fluctuations are not optional. They are built into the uncertainty principle. If you sum those zero-point energies naively, the predicted vacuum energy would curve space-time violently, because energy tells space how to bend. The universe would either rip apart instantly or collapse, neither of which happened, so the calculation cannot be the whole story. So something is missing in our understanding of how vacuum energy gravitates, and the possibilities are unsettling. Either the calculation is incomplete, or cancellations occur, or gravity responds differently than expected, and each option hints at deeper structure beneath known physics. The catastrophe is not a small numerical quibble, because the gap is not a factor of 2 or 10. The gap is many orders of magnitude, so large it looks like a signpost toward deeper laws, as if the universe is daring us to find the missing principle. This is where awe becomes methodological tension, because the measurements are solid even when the interpretation is not. We can measure dark energy's effect on expansion, yet we cannot explain its value from first principles, and that mismatch sits at the center of modern cosmology. Cosmologists therefore treat dark energy as a parameterized component and ask what observations can constrain, because the sky can adjudicate between competing ideas. The key quantity is the equation of state parameter called W, which compresses complicated microphysics into a single, testable number. W is defined as pressure divided by energy density for the dark component, and it controls how that component evolves as the universe expands. For a cosmological constant, W equals -1, which corresponds to a constant density and a persistent negative pressure. If W differs from -1, dark energy might evolve with time, and that would be a crucial clue. It would point away from a pure constant and toward a dynamic field or new physics, something with its own history, not merely an unchanging background term. Measurements of W come from combining supernova distances, galaxy clustering, and the CMB, because no single probe is decisive by itself. Each probe samples a different era and helps break degeneracies, so the constraints tighten when the datasets agree. The story now pivots from what the universe contains to what shape it has, because geometry is not decoration. Curvature changes how distances and volumes behave, and it changes how a fixed physical ruler appears when projected across the sky. Fact 18. On the largest scales, the universe appears geometrically close to flat. That means the total energy density is very close to the critical density. Curvature can be explained without advanced math by thinking about triangles, and by imagining drawing them with beams of light. In flat space, the angles of a triangle add to 180 degrees, and parallel lines stay parallel forever. In positively curved space, like a sphere, triangle angles add to more than 180 degrees, and straight lines eventually converge. In negatively curved space, like a saddle, they add to less, and lines diverge as if the surface is spreading beneath them. Spacetime curvature also affects how light travels and how the CMB's acoustic peaks appear, because those peaks encode a known physical scale from the early universe. The peak spacing acts like a ruler projected across the sky, and the geometry tells us whether that ruler looks larger or smaller than it should. Planck and other measurements show that ruler fits a nearly flat geometry, and the agreement is visually striking in the data. Flatness does not mean infinite for sure, but it implies curvature is small within our horizon, so any global bend is gentle on observable scales. Flatness also links back to the energy budget, and this is where the accounting becomes unavoidable. If the universe is flat, then matter, radiation, and dark energy must sum to the critical value, like weights balancing precisely on a cosmic scale. That bookkeeping is one reason dark energy became unavoidable, even for skeptics of the supernova result. Without it, the measured matter content would leave the universe noticeably open and curved, and the CMB would not match the observed peak pattern. So 3 ideas lock together, and the fit is tighter than any one measurement alone could provide. Supernovae show acceleration, the CMB favours flatness, and structure growth constrains matter, leaving dark energy as the dominant remainder. Now we face the existential menu of futures, each tied to how dark energy behaves, and each future has a distinct physical signature. The far future is not guessed from philosophy, but from W and its evolution, and from whether the dark sector remains stable. If W equals -1 and stays constant, expansion accelerates forever, and the universe becomes increasingly dilute. Galaxies drift apart, star formation dwindles as gas is used up or heated, and the universe approaches heat death as temperature differences fade. This is the Big Freeze, also called heat death, where usable energy becomes scarce and complexity becomes harder to sustain. Not everything ends suddenly, but everything trends toward thinness and darkness, and the most dramatic events become rarer with each passing eon. In that future, local bound systems remain intact for a long time, because gravity still wins on small scales. The Milky Way and its neighbours stay gravitationally bound, even as the cosmic background empties, and the local group becomes an island universe in an ever-expanding sea. If W is less than -1, a scenario called phantom energy, acceleration strengthens with time, and the expansion rate can diverge in finite time. The mathematics implies a scale factor that blows up, and the repulsive effect grows without bound. That leads to the Big Rip, where even bound structures are eventually torn apart because the stretching overcomes every binding force. First clusters unbind, then galaxies, then solar systems, and finally atoms, until even the concept of a stable object loses meaning. The Big Rip is dramatic, but it is not currently required by data, and the best fit values still hover near -1. It remains a possibility if W is below -1 and stays there, and that stays there is the crucial observational challenge. If W is greater than -1 and evolves, acceleration could weaken, and the far future becomes less extreme. The universe could still expand forever, but more gently, or approach a different asymptotic state where expansion continues without tearing structures apart. There is also the possibility of a future phase change in the dark sector, and that idea echoes known transitions in physics. a field could shift to a new vacuum state, altering the effective cosmological constant and changing the expansion rate in a way that would feel sudden on cosmic timescales. A phase change could speed expansion, slow it, or even trigger contraction in some models depending on the new vacuum energy. The point is that cosmic destiny depends on microphysics we do not yet know, and the sky is the only arena where those microphysical choices reveal themselves. This uncertainty is not ignorance in the casual sense, because it is bounded and quantified. It is a precise ignorance bounded by measurements, with error bars that shrink as surveys improve, and with systematic uncertainties that are hunted as aggressively as statistical noise. Supernova programs now map thousands of events, and they refine calibration using light curve shapes and host galaxy properties, because environments can subtly affect brightness. The goal is to reduce systematics, not just add data, so that the inferred acceleration is anchored to robust astrophysics. Baryon acoustic oscillations provide another distance ladder, using the same early universe sound horizon imprinted in galaxy clustering, and that imprint is remarkably stable. That ruler crosschecks supernova distances, and it ties late-time expansion back to the physics of the primordial plasma. Weak lensing maps the growth of structure over time, which depends on both dark matter and dark energy, and it does so through tiny distortions in galaxy shapes. Growth history can distinguish a cosmological constant from modified gravity, because changing gravity alters how quickly clumps form even if distances look similar, because acceleration could also signal that gravity changes on large scales, and that possibility remains scientifically live. Some theories mimic dark energy by altering how space-time responds to matter at cosmic distances, effectively changing the rules rather than adding a new component. So the core question becomes sharper, and it is as philosophical as it is technical. Are we seeing a new energy component, or are we seeing a breakdown of general relativity on the larger scales, where our tests have historically been weakest? Either answer reshapes what exists beyond what we can see, and it reshapes what we mean by content in the universe. A new field would add unseen inventory, and modified gravity would change the rules that govern everything visible, from galaxy motions to the fate of horizons. The narrative tension is therefore not only about fate, but about reality's inventory, and about the limits of inference. We can weigh the universe, yet we do not know what most of it is, and that is a rare situation in science. High precision paired with deep ambiguity. This is the same pattern we saw with dark matter, now amplified by the scale of the dominance. Dark matter is unseen mass that clumps, and dark energy is unseen influence that smooths and accelerates, and together they tell us the luminous universe is not the main act. Together they imply that the luminous universe is a minority report, a bright trace within a much larger ledger. The cosmos is dominated by components we infer indirectly through geometry, motion, and statistical patterns, and those patterns must be read with care. That indirectness is not weakness, it is the method of cosmology, and it is surprisingly rigorous. We cannot sample the universe in a lab, so we use the sky as a controlled experiment, where different lines of sight act like repeated trials. The sky provides repeated trials across billions of galaxies, and across enormous spans of time encoded in redshift. Each supernova, lensing shear field, and CMB map is a data point in a single coherent model, and the model's consistency is itself a form of evidence. Yet the model's success creates its own discomfort, because it can feel like bookkeeping without understanding. We can fit parameters exquisitely, while still lacking a physical explanation for the dominant term, and that gap is where the next breakthroughs must land. So what do we actually know about dark energy, when we strip away the name and keep only the measurements? We know it is smooth on large scales, it drives acceleration, and it behaves close to W equals -1 within current uncertainties. We also know it does not clump like matter, or it would distort structure in ways we do not observe, and it would leave fingerprints in lensing maps. Its influence is strongest where matter is thinnest, in the cosmic average, and that smoothness is one of its defining observational traits. What we do not know is whether it is vacuum energy, a dynamic field, or a sign of modified gravity, and each option implies different physics at a fundamental level. We do not know why its density is small but non-zero, and we do not know what principle sets that scale. We also do not know why dark energy becomes dominant only in the recent universe, and that timing is not trivial. That timing problem is sometimes called the coincidence problem, because it seems oddly convenient that we live near the handoff between matter domination and dark energy domination. The coincidence is that we live near the era when matter and dark energy densities are comparable, which is a narrow window on a logarithmic timeline. Earlier, matter dominated, and later dark energy dominates overwhelmingly, so why should observers appear near the transition? That coincidence tempts anthropic arguments, selection effects, and multiverse ideas, because those frameworks can turn "why now" into "because otherwise no one asks." It also motivates more conservative searches for dynamical explanations, where dark energy tracks matter for a while before diverging. For this documentary's central question, the implication is double-edged, and it lands with a quiet weight. The universe can build life from stardust, yet the universe's largest scale behavior is governed by something we cannot name, and that should humble any claim of completeness. Meaning and origins therefore sit inside an accelerating backdrop, and the backdrop is not passive scenery. The future visibility of the cosmos is not guaranteed, and the accessible universe may become smaller with time, even if the universe itself grows without bound. Even now, acceleration creates a cosmic event horizon, and it is a limit with consequences for knowledge. There are galaxies whose present light will never reach us, because space expands too quickly in between, stretching the path faster than photons can close the distance. That horizon is not a wall, it is a limit set by dynamics, and it depends on the future behavior of dark energy. It is a reminder that knowledge depends on both physics and timing, and that the universe can hide its own history by accelerating away from it. So the runaway universe is not only a fate story, it is an epistemology story about what can be known. It is a story about what kinds of questions remain answerable in principle, and which answers require that we live in a particular cosmic era. If acceleration continues, the far future sky becomes emptier, and cosmology becomes harder for any future observers, no matter how intelligent they are. The evidence for the Big Bang could fade from view, leaving only a local galaxy and a cold, nearly featureless background. That thought loops back to our moment, and it changes the emotional colour of the data. We live at a time when the universe still displays its history openly, and we can still measure the parameters that govern destiny, before the expansion erases the clues. The chapter's core facts now converge, and they converge with an unsettling elegance. Acceleration is measured, dark energy dominates the budget, vacuum energy theory fails catastrophically, and geometry is close to flat, and the combination is both coherent and mysterious. From those facts, the futures branch, and the branching is not arbitrary. Big freeze is likely under a constant W, big rip is possible if W is below -1, and phase changes remain open, because the microphysics could still surprise us. The honest conclusion is not despair, it is precision, and precision is a form of progress. We can measure dark energy's fingerprints, but we cannot yet identify the hand that left them, and that gap is where the next chapters gain urgency. To probe the deepest laws, we go to the most extreme laboratories in nature, where gravity pushes physics to its limits, and where space-time itself becomes a dynamic actor. Transition. From the universe's fate, we move to its fiercest engines, and we enter the realm of black holes. From the universe's fate, we move to its fiercest engines, and we enter the realm of black holes. Black holes feel like endings, yet they are also measurements of gravity pushed to its mathematical limit. They turn the central question into a test: what exists beyond what we can see when even light can be trapped? On screen, the familiar sky dims, and a dark circle sits where stars should be. Around it, a thin ring of light trembles, as if reality is being stretched into a lens. A black hole begins with collapse, when pressure and motion can no longer resist gravity's inward accounting. In stellar cases, a massive star exhausts its nuclear fuel, loses thermal support, and its core caves inward. The outer layers can rebound as a supernova, while the core continues falling, compressing matter to densities that defy intuition. In supermassive cases, growth is slower and less theatrical, fed by mergers, repeated inflows, and long-term accretion over cosmic time. Historically, the idea sounded like a paradox before it sounded like an object. In the late 18th century, thinkers like John Michell imagined dark stars, where light could not escape. The modern black hole emerged from Einstein's relativity and from Karl Schwarzschild's early solution, which showed how gravity reshapes time and distance near a compact mass. We do not see the hole itself, because it emits no light from within its boundary. We see its influence on nearby matter, on light paths, and on timekeeping. The universe hides the object, then reveals it through consequences, like footprints in snow that outline an invisible animal. In visual terms, we watch stars curve around an empty center, and we watch gas glow as it spirals into darkness. Fact 19. An event horizon is a one-way boundary, defined by escape velocity reaching light speed. Escape velocity is the speed needed to climb out of a gravitational well without falling back. When that required speed equals c, outward paths stop being possible. The horizon's size is set by mass, and for a non-spinning black hole it scales simply with it. This is not a material surface, and it is not a hard shell in space. It is a geometric boundary in space-time, where the future direction points inward. Inside, every possible future path leads deeper, like time itself has been reoriented. The boundary is defined by causality, not texture, which is why it can be crossed without hitting anything. In Newton's language, gravity is a force, and light is a fast projectile. In Einstein's language, gravity is curvature, and light follows the straightest paths available. Near a black hole, spacetime is curved so strongly that outward light cones tip inward. The diagram is simple, but its meaning is severe. Outward becomes a direction that no longer points to tomorrow. So nothing escapes is not a slogan about suction or a cosmic vacuum cleaner. It is a statement about geometry and causality. Light cannot climb out because there is no outward route that still points toward the future. Even a photon fired straight up is still carried inward, because the space it travels through is shaped like a funnel of time. The horizon also marks a limit on information we can receive from a region of space-time. Signals can approach it, redshift, and fade as their clocks appear to slow relative to ours. The last photons arrive stretched and weakened, like a message losing energy as it tries to leave. In a visualization, the light shifts from blue to red to infrared, then slips below our instrument's reach. Time dilation is not an optional effect near a black hole, it is built into the metric. Clocks deeper in the gravitational well tick more slowly relative to distant observers, and that difference can be computed precisely. The closer you hover to the horizon, the more extreme the mismatch becomes, until hovering itself demands impossible acceleration. The physics is plain language simple. Gravity makes time run differently, and near a horizon it does so dramatically. For an infalling traveller, the horizon can be crossed without a local alarm in many cases. For a distant observer, the traveller appears to slow and dim, never quite completing the crossing. Both descriptions are consistent because they compare different time coordinates, and relativity allows different slices of space-time to tell different stories. The tension is not a contradiction, but a reminder that now is not universal. This is where black holes become narrative engines rather than mere monsters. They force us to separate what is locally experienced from what is globally observed. They make what is real depend on how space-time is sliced into moments. In the visuals, we cut between a falling camera that sees nothing special and a distant telescope that watches the fall freeze into a fading ember. Yet black holes are not rare curiosities, and that is the next shock. They appear to be woven into the architecture of galaxies and into the history of structure formation. They are extreme, but they are not exotic in the sense of being uncommon. The universe seems to manufacture them as naturally as it manufactures stars. Fact 20. Supermassive black holes sit in the centers of most large galaxies. The Milky Way hosts one, Sagittarius A, with a mass of about 4 million suns. Other galaxies hold monsters billions of times the Sun's mass. Their horizons can be larger than the orbit of Mercury, and their gravitational reach shapes the motion of entire nuclear star clusters. The evidence comes from stellar orbits, gas dynamics, and compact radio and infrared sources. Near our center, stars whip around an unseen point, tracing Keplerian ellipse around a tiny volume, some complete orbits in mere decades, which is astonishing on galactic scales. The implied mass is too large and too concentrated to be anything else, because no cluster of normal stars could remain so compact without dispersing. This connection reshapes galaxy evolution, because the central black hole correlates with the galaxy's bulge. The bigger the bulge, the bigger the black hole, suggesting coevolution rather than coincidence. Feedback from the nucleus can regulate star formation across the whole galaxy, altering how quickly gas cools and how efficiently it collapses into new suns. The galaxy is not just a backdrop for the black hole, It is a partner in a long gravitational negotiation. When a supermassive black hole is actively feeding, the galaxy can become an active galactic nucleus. Gas spirals inward, heats, and radiates across the spectrum, sometimes outshining the galaxy's stars. Quasars are AGN seen at high luminosity and great distance, marking early growth when the universe was younger and gas-rich. In archival imagery, we see point-like beacons that look like stars, yet their spectra reveal engines far more powerful. Accretion is the key, because black holes are dark but their meals are bright. Matter falling in does not drop straight down like a stone, because it carries angular momentum. It forms an accretion disk, a rotating flow that must shed energy and momentum to move inward. The disk is a traffic jam in orbit. Material wants to fall, but it must first give up its sideways motion. Friction, turbulence, and magnetic stresses heat the disk to extreme temperatures. The inner disk can glow in X-rays, while outer regions radiate in optical and ultraviolet. The brightness is powered by gravity, converting infall into radiation with high efficiency, often higher than nuclear fusion in terms of energy per unit mass. In a close-up visualization, the disk's inner edge blazes white-blue, and hotter patches flicker as instabilities ripple through the flow. This is where danger and awe meet in a measurable way. The same physics that built atoms in stars can be overwhelmed by gravity's bookkeeping. In the disk, matter is ionized, shredded, and accelerated, becoming a plasma that responds to magnetic fields. Temperatures rise until electrons and nuclei separate, and the gas becomes an electrically conducting fluid that can carry currents. Those currents, in turn, strengthen magnetic fields, creating a self-amplifying dance. Black holes also add a new variable that stars do not share in the same way. They can rotate, and rotation changes what spacetime itself does. The black hole's spin is not a surface spinning like a planet, but a property of the spacetime solution. It is an angular momentum written into geometry. Fact 21. Black holes can spin, dragging spacetime around them through frame dragging. In general relativity, a rotating mass twists nearby spacetime, like a whirlpool in geometry. Near a spinning black hole, rest becomes impossible, because spacetime itself is being pulled around. Even the direction of possible orbits is biased, and the difference between co-rotating and counter-rotating paths becomes stark. The region outside the horizon where this effect dominates is called the ergosphere. Inside the ergosphere, all observers are forced to co-rotate, even if they try to resist. Energy can, in principle, be extracted from the spin, because rotation stores usable energy in the geometry. The ergosphere is a region where the rules feel inverted. Objects can still escape, yet they cannot remain stationary. Spin matters because it changes the inner edge of the accretion disk and the efficiency of radiation. A rapidly spinning black hole allows stable orbits closer in, where gravity is stronger and energy release is higher. That shift changes the disk's temperature profile, its spectrum, and the timing of its flickers. Spin also sets the stage for launching jets, turning rotation into collimated power through magnetic structures that act like cosmic wiring. Frame dragging is not only theoretical, it has indirect observational support in disk behavior and jet alignment. It also echoes a theme from earlier chapters, where unseen structure is inferred from motion and geometry. Here, the invisible is not matter, but the twisting of space-time itself. The camera can show a grid of space-time twisting like fabric around a spinning drain, then snapping back into the calm of distant space. If the horizon is the boundary, then tidal forces are the texture of the approach. Gravity is not uniform across an object, and that gradient becomes lethal near compact masses. The closer you get, the more the field changes from head to toe, and the more your body becomes a measurement device for curvature. Fact 22. Tidal forces can spaghettify matter, stretching it along one axis and squeezing it along others. The effect comes from differential gravity, where your near side feels a stronger pull than your far side. The result is elongation, compression, and eventual disruption. It is not a single pull, but a difference in pull, and that difference is what tears structures apart. What you would experience depends strongly on black hole mass. Near a stellar mass black hole, the horizon is small, so the gravitational gradient at the horizon is enormous. Spaghettification can occur outside the horizon, meaning you are torn apart before crossing. In imagery, a falling object becomes a thin filament, glowing as it heats, then dissolving into a stream of plasma. Near a supermassive black hole, the horizon is vast, so the gradient at the horizon can be comparatively gentle. You could cross the horizon without immediate shredding, at least in principle, because the tidal forces scale inversely with mass at the horizon. The violence is postponed to deeper regions, where curvature grows again and where no signal can report what happens. The calm at the boundary is unsettling because it hides the certainty of what comes later. This contrast is counterintuitive, and it teaches a rule of extremes. Bigger black holes can be safer at the boundary, even though they are more massive. The danger is not mass alone, but how concentrated that mass is in space. In other words, density and curvature decide the outcome, not the headline number of solar masses. Accretion, spin, and tides set the stage for the most dramatic outward sign of a black hole. Some of the most powerful structures in the universe are not things falling in, but things being thrown out. The engine is fed by infall, yet it announces itself by escape. Fact 23. Black holes can launch jets thousands of light years long. These jets are narrow beams of plasma accelerated to near light speed, often emerging perpendicular to the accretion disk. They can punch through a galaxy and inflate lobes far beyond the visible stars. In wide shots, the host galaxy looks delicate, while the jets look like rigid blue spears drilling into intergalactic darkness. Jets require magnetic fields, rotation, and a conducting plasma. In the disk, magnetic field lines can be wound up by differential rotation, storing energy like a twisted spring. Near the spinning hole, frame dragging can help organize and amplify fields, channeling energy into a focused outflow. The plasma follows the field like beads on wires, and the overall structure becomes self-collimating, narrowing as it accelerates. The jet's apparent brightness can be boosted by relativistic beaming. When plasma moves toward us at near light speed, its radiation is concentrated into a narrower cone. This makes some jets look brighter and more variable, depending on viewing angle. A small change in orientation can turn a modest source into a blazing beacon, which is why some active galaxies appear to flare with almost impossible intensity. Jets are not decorations, they are feedback mechanisms that reshape galaxies and clusters. They can heat surrounding gas, prevent it from cooling, and regulate star formation by starving the galaxy of fresh fuel. In clusters, jets can carve cavities in hot gas, leaving imprints that persist for millions of years. The aftermath can be mapped in X-ray images as bubbles and ripples, like scars left in a glowing atmosphere. So black holes are not only sinks, they are engines that couple small scales to large ones. A horizon measured in kilometers can influence structures measured in light years. The universe builds extremes, then uses them to rearrange its own matter. It is worth pausing on the implication: how many galactic histories were quietly rewritten by a central object we cannot directly see? This is where the chapter's tension sharpens into a paradox about information. If nothing escapes, what happens to the information carried by matter that falls in? Quantum mechanics says information should not be destroyed, while classical black holes seem to erase it behind the horizon. The question is not about memory in a human sense, but about whether the universe keeps a complete accounting of physical states. That conflict is not philosophical, it is a technical clash between two successful frameworks. General relativity treats the horizon as a causal boundary that hides internal details. Quantum theory treats evolution as reversible in principle, preserving information even when it is scrambled. Both frameworks have been tested with extraordinary precision, which is why their disagreement feels like a fault line under the foundations. Hawking radiation adds another twist, suggesting black holes can slowly evaporate. Quantum fields near the horizon can produce radiation that carries energy away, making the black hole lose mass over immense timescales. If a black hole evaporates away, the question becomes unavoidable. Does the information return in the radiation, or is it lost, implying a breakdown of quantum rules? Modern ideas propose that information is not destroyed, but encoded in subtle correlations. The horizon may act like a processor, not a shredder, scrambling inputs into outputs that are hard to decode. The details remain debated, but the stakes are clear because they touch the foundations of physics. The unsettling possibility is that nature hides information in patterns so fine that, for practical observers, it is as good as gone. Black holes therefore answer the central question in an unexpected way. Beyond what we can see is not only more stuff, but deeper rules about space, time, and causality. The universe does not merely hide objects, it hides mechanisms and then leaks clues through extreme environments. The clues arrive as orbits, spectra, shadows, and jets, observable signatures that translate invisible geometry into light. We return to the opening hook with a darker mirror. Stardust built our bodies, but gravity can unbuild matter into heat, light, and motion near a horizon. The same cosmos that assembles complexity also tests its limits, and it does so with consistent laws. When we watch gas glow as it falls, we are watching gravitational energy being converted step by step into radiation we can record. Black holes also connect back to dark matter and dark energy by method rather than substance. We infer them through motion, lensing, and geometry, then confront what the inference implies. Here, we infer a boundary where our usual intuitions about time and escape fail. The pattern is familiar. The universe does not hand us answers directly, but it leaves measurable distortions in the behavior of what we can see. The chapter closes with a final pivot from stillness to vibration. If black holes bend spacetime so strongly that horizons form, then spacetime is not rigid. It can carry disturbances. In the final visual, the dark silhouette recedes, and the background grid begins to quiver, as if the universe itself were a drumhead. For centuries, we learned the universe by collecting photons, then translating colour into temperature, motion, and chemistry. We built the cosmic story from spectra, thin rainbows split by prisms and gratings, where dark absorption lines reveal which atoms sit in a star's atmosphere. We measured Doppler shifts to infer speed, and we tracked brightness to estimate distance, even when the numbers were uncertain. Yet light is only one messenger, and it can be blocked, scattered, or never emitted at all. Dust clouds can hide a stellar nursery, and a black hole merger can occur in near darkness with little to photograph. The central question sharpens here, because astronomy is not only about images, it is about evidence, what exists beyond what we can see when the universe communicates through geometry itself. Fact 24. Gravitational waves are ripples in spacetime predicted by general relativity, produced by accelerating masses and confirmed by direct detection. In Einstein's view, gravity is not a force in the usual sense, but the curvature of spacetime produced by mass and energy. His field equations do not merely describe static curves around planets, because they also permit spacetime to change and propagate. When mass distributions accelerate asymmetrically, the changing curvature can travel outward as a wave solution. These waves move at light speed, carrying energy and information away from the source, even from regions where light is trapped. The prediction was controversial for decades, partly because coordinates can mislead, and partly because the effect seemed impossibly small. Over time, the mathematics clarified, and the physical meaning became unavoidable. Space-time itself can ripple. A gravitational wave is not a sound wave moving through space because it needs no medium. Sound is a pressure disturbance in air or water, while a gravitational wave is an oscillation of the metric that defines distance and time. The wave produces a periodic stretching and squeezing of separations, as if the ruler used to measure space briefly changes its calibration. Two free objects separated by space will find their separation change, even if no local push or pull acts on them. In plain terms, the space between them alternately lengthens and shortens in a pattern that passes through. The effect is tiny because gravity is weak compared with the other forces, and because astrophysical sources are far away. Even a violent merger, releasing immense energy, arrives at Earth as a faint tremor. The key quantity is strain, written as h, the fractional change in length. Strain equals the change in distance divided by the original distance, and it is dimensionless, like a percentage written without units. This matters, because a wave does not announce itself by an absolute displacement, but by a proportional distortion across whatever baseline you build. A wave with h of 10 or 21 changes a 4-kilometer baseline by far less than a proton's diameter. Put differently, it changes that length by about 1 part in 1,000 billion billion, a ratio that strains everyday intuition. That is why detection took a century of theory, engineering, and patience, as well as a willingness to treat measurement as an art. The difficulty is not only smallness, it is noise that imitates signals. Earthquakes send low-frequency motion through bedrock, and ocean waves generate microseisms that never fully stop. trucks on distant roads, wind on buildings, and even human activity can shake the ground in ways that leak into instruments. Thermal motion in atoms causes mirrors and suspensions to jitter because temperature is microscopic vibration. Quantum fluctuations in light add uncertainty because even a perfect laser has statistical noise in photon arrival. The detector must separate a real space-time ripple from every local vibration, and do it with statistical confidence. The universe is whispering, and the planet is loud, so the analysis must be as disciplined as the hardware. So gravitational wave astronomy begins as a measurement problem, not a telescope problem. We are not forming images, we are tracking distortions in distance with extreme precision, and then reconstructing a source from a time series. The method is indirect, like dark matter and dark energy, but it's also brutally quantitative. Either space-time stretched by that amount at that time, or it did not, and the data must show the difference. This is why the field grew alongside advances in lasers, vacuum technology, vibration isolation, and computation. It also grew alongside a culture of skepticism, because extraordinary claims require an audit trail. Fact 25. LIGO and Virgo measure changes smaller than a proton across kilometre-scale arms using laser interferometry. Each detector is an L-shaped instrument with long evacuated tubes, mirrors at the ends, and a laser split into two paths. Visually, the site looks like a geometric scar on the landscape. Two straight corridors vanishing to the horizon, fenced and silent. Inside the tubes, air is removed to create an extreme vacuum, so that molecules do not buffet the light. The beams travel down the arms, bounce many times between mirrors, then recombine at a photodetector. The mirrors are polished and coated to extraordinary smoothness, because even tiny surface imperfections scatter light and add noise. Interferometry turns distance into light and dark by exploiting the wave nature of light. If the two paths are exactly equal, the returning waves cancel in a controlled way, producing near darkness at the output, a condition called destructive interference. The darkness is not failure, it is sensitivity, because small changes then produce noticeable brightening. If a gravitational wave passes, one arm effectively lengthens while the other shortens, changing the phase of the light. The cancellation becomes imperfect, and a flicker appears that encodes the strain pattern. That flicker is not a picture of the source, but it is a precise fingerprint of the motion that produced it. The baseline is kilometers, but the effective path is much longer because the light bounces repeatedly. In practice, the arms act like optical cavities, storing light so it samples the changing distance many times before exiting. The mirrors are suspended like pendulums to isolate them from ground motion, and multi-stage suspensions act as filters that reduce vibration at the frequencies of interest. The vacuum removes air fluctuations, and temperature control reduces thermal drift that would otherwise mask signals. Multiple detectors are essential because a real wave must arrive at separated sites with consistent timing and shape. Coincidence across the network is how the signal becomes believable, and how the sky position can be narrowed. Even then, the measurement is limited by fundamental physics, not only by craftsmanship. At high frequencies, photon shot noise makes the light's phase uncertain, because photons arrive discretely rather than as a perfectly smooth stream. At low frequencies, radiation pressure noise and seismic noise dominate, pushing the instrument in slow drifts that are hard to subtract. Engineers tune lasers, coatings, suspensions, and control systems to carve out a quiet band where the universe can be heard. The detector is therefore both a physics experiment and a listening device, balanced between competing noise sources. When sensitivity improves, the observable universe for mergers expands dramatically, because volume grows with the cube of distance. The payoff is that the waveform is a direct record of gravity in the strong field regime. The signal rises in frequency and amplitude as two compact objects spiral together, because orbital speed increases as separation shrinks. Energy and angular momentum are carried away by gravitational radiation, so the orbit decays in a predictable way. This chirp is not an artistic metaphor. It is a calculable pattern predicted by general relativity and refined by numerical simulations. Matching observed chirps to templates allows masses, spins, and distances to be inferred, along with clues about orbital orientation. The analysis is like fitting a musical score to a faint recording, where the notes encode the system's parameters. The first direct detection in 2015 was not a new kind of light, it was a new kind of evidence. Two black holes merged more than 1 billion light-years away, and their final moments shook space-time enough to be measured on Earth. The event arrived as a brief rising tone in the data, lasting only a fraction of a second, yet containing a complete dynamical story. The detection confirmed a key prediction of relativity, and opened a channel that does not depend on an electromagnetic emission. It also proved that heavy black hole binaries exist and merge within the age of the universe, reshaping models of stellar evolution. Behind the scenes, it validated decades of work, including earlier indirect evidence from binary pulsars that lost energy exactly as gravitational radiation predicts. Fact 26. Black hole mergers convert mass to energy in a burst that can outshine all stars combined for a moment. The power is gravitational, not luminous, because most energy leaves as space-time waves rather than photons. The conversion is described by E equals mc squared, where a small mass difference becomes an enormous energy release. In a typical event, several solar masses can be radiated away as gravitational waves in less than a second. That does not mean matter is ejected like debris, because black holes have no surface to explode. It means the system's total mass energy, measured from far away, decreases because energy has been carried off by the waves. This is a new way to weigh black holes, and it is remarkably direct. The inspiral reveals the chirp mass, a particular combination of the two masses that governs how quickly the frequency rises. The merger and ring down reveal the final mass and spin, because the remnant's geometry determines how it vibrates. The difference between initial and final mass reveals the radiated energy, turning the waveform into an accounting ledger. The remnant black hole settles by ringing like a struck bell, emitting damped oscillations called quasi-normal modes. Measuring those modes tests whether the object matches the Kerr black hole predicted by relativity, with no extra hair beyond mass and spin. These tests matter because black holes are where gravity is most extreme and least previously tested. Solar system experiments probe weak fields, where space-time curvature is gentle and equations can be approximated. Binary pulsars probe strong gravity, but with slower dynamics, so the nonlinear regime is sampled indirectly. Mergers probe rapid, nonlinear space-time behavior where alternative theories could diverge, especially near the moment horizons form a single surface. So each detection is not only an astrophysical story, it is a physics experiment conducted at cosmic scale. The question beneath the data is simple and profound. Does space-time behave exactly as Einstein described when pushed to its limits? Yet black holes are only one side of the collision story, because not all compact objects are empty horizons. Neutron stars are different laboratories because they contain matter at nuclear density, compressed beyond what any terrestrial experiment can sustain. They are supported by degeneracy pressure and nuclear forces, and their internal structure depends on the equation of state of dense matter. A teaspoon of neutron star material would outweigh a mountain, yet the star is only about the size of a city. When neutron stars merge, the signal carries information about tidal deformation and radius, not just mass. Those tidal effects subtly alter the late inspiral, leaving a measurable imprint in the phase evolution. Fact 27. Neutron star mergers forge heavy elements like gold and platinum and create kelonovae. In ordinary stars, fusion builds elements up to iron, because heavier fusion consumes energy instead of releasing it. The heaviest elements require rapid neutron capture, the R process, in environments flooded with free neutrons. Neutron star mergers provide that environment when neutron-rich matter is ejected and decompresses. The ejection can come from tidal tails and shock-heated outflows, and the details depend on the masses, spins, and the stiffness of dense matter. As the ejected material expands, nuclei capture neutrons faster than they can decay, building very heavy isotopes in a runaway sequence. Those isotopes then decay towards stability, releasing energy that powers a transient glow, because radioactive decay heats the expanding debris. That glow is a killer nova, dimmer than a supernova but still visible across many galaxies, especially in sensitive surveys. The colour evolves as opacities change, because lanthanides and other heavy elements absorb light differently than lighter elements. Early emission can appear bluer if the ejector is relatively lanthanide poor, while later emission reddens as heavier element opacities dominate. In visuals, the light curve is a fading ember that changes hue as it cools and thins. This connects cosmic chemistry to the opening hook about stardust and life, and it makes the abstract intimate. Some fraction of the gold in jewellery and the platinum in the electronics likely came from ancient mergers, not from the Sun's fusion. The atoms were not crafted gently, but assembled in milliseconds amid extreme gravity and neutron flux. The universe does not only build atoms in stars, it also builds rare elements in catastrophic collisions. Everyday matter becomes a fossil record of events that occurred long before Earth existed, embedded in rocks, oceans, and bodies. When we hold a precious metal, we are holding a relic of a violent astrophysical past. The 2017 event GW170817 made this connection concrete, and it did so with dramatic timing. Gravitational waves announced a neutron star merger, and telescopes found a counterpart in a nearby galaxy after a rapid search. Gamma rays arrived seconds later, and optical and infrared light followed over days, fading and reddening as predicted. The combined dataset linked short gamma ray bursts to neutron star mergers and confirmed kilonova models. It also showed how coordination transforms discovery, because dozens of observatories turned toward the same patch of sky. In narration, it is a relay race of signals, first geometry, then high-energy light, then the slower afterglow. This is multi-messenger astronomy, and it changes how we locate and interpret cosmic events. Gravitational waves provide distance and a coarse sky region, while light provides precise localization and environmental context. Neutrinos, when detected, can reveal particle processes in dense, hot regions that photons cannot escape, because they pass through matter with little interaction. Each messenger carries different biases, and together they reduce ambiguity, turning a single detection into a richer narrative. The same event can be both a gravitational waveform and a chemical factory, both a test of relativity and a clue to galaxy evolution. Multi-messenger observations also test fundamental physics, because they compare different carriers of information across cosmic baselines. Comparing arrival times of gravitational waves and gamma rays constrains whether gravity travels at light speed, and it limits how much any deviation could accumulate. The waveform's phase evolution tests whether gravitons have mass, because a massive graviton would disperse waves by frequency, slightly delaying lower frequencies. Joint observations can also probe violations of Lorentz invariance and constrain alternative gravity models. These are subtle tests, but the distances are so large that tiny effects would have time to reveal themselves. The universe becomes a laboratory where the baseline is measured in millions of years. There is also a cosmological application that echoes Chapter 4's focus on expansion, and it uses geometry in a new way. Gravitational wave sources can act as standard sirens, because the waveform encodes absolute luminosity distance without a distance ladder. The amplitude weakens with distance in a way that can be modelled once the system's intrinsic parameters are inferred. If an electromagnetic counterpart identifies the host galaxy, redshift can be measured independently from spectral lines. Distance and redshift together constrain the Hubble constant and expansion history, offering a cross-check on existing tensions. The promise is not only a new number, but a new method with different systematics. So the new sense does not replace light, it complements it, and it exposes what light hides. Dusty regions that obscure optical telescopes do not block spacetime waves, because the waves are distortions of spacetime itself. Black hole mergers can be nearly dark electromagnetically, yet loud gravitationally, and that contrast is scientifically valuable. The universe has channels of information that operate even when photons fail, and the best understanding comes from comparing them. In visuals, the scene shifts from a bright telescope dome to a quiet interferometer, where the image is a line on a graph. The deeper tension is that we may be hearing signals from earlier times than any light can reach, which reframes what seeing the past means. The cosmic microwave background is the oldest light we can see, released when the universe became transparent about 380,000 years after the Big Bang. Before that, photons were trapped in plasma and scattered constantly, erasing direct visual memory like fog that never clears. Gravitational waves, by contrast, interact extremely weakly, so they can pass through the early universe with far less scattering. In principle, they can carry a record from epochs that are electromagnetically opaque. The question becomes not whether information exists, but whether we can build instruments quiet enough to retrieve it. That raises a frontier possibility, one already hinted at by inflationary theory and early universe physics. There could be a background of primordial gravitational waves from the universe's first instance, carrying information from energies far beyond any accelerator. Such waves would be a fossil of processes that occurred before atoms, before stars, and before the CMB's last scattering surface. Detecting them would be like hearing the universe clear its throat before it spoke in light. It would also force us to confront how quantum fluctuations could be stretched to cosmic scales, leaving a pattern imprinted on spacetime itself. What would it mean if the earliest whisper is still present, diluted but not erased? But the challenge scales with the promise, because the signal would not arrive as a single dramatic chirp. Primordial signals would be faint, spread across frequencies, and mixed with astrophysical backgrounds from countless unresolved mergers. Separating them requires long observations, better detectors, and careful modelling of foregrounds, so that the hum of the modern universe can be subtracted. It also requires humility, because a non-detection still constrains early universe physics, narrowing what inflation could have been. In science, silence can be informative, but only if the listening is rigorous. The narrative arc now tightens around a single idea, and the idea is methodological as much as it is cosmic. We're expanding our senses, from seeing the universe to hearing its geometry, and each new sense reveals a deeper layer. Dark matter was inferred from motion, dark energy from expansion, and gravitational waves from strain, all through patterns rather than pictures. The pattern is consistent, and it is a reminder that reality is not obligated to be visually obvious. The universe is stranger than intuition, yet it is legible through measurement, provided we accept indirectness as a strength. Each new channel also forces new questions about what we've been missing. Gravitational wave detections also reshape what black holes mean in the cosmic story, because they change invisibility into audibility. In Chapter 5, black holes were defined by horizons and invisibility, and by indirect evidence from accretion and orbits. Now they become audible, because mergers radiate their dynamics into spacetime itself, and the waveform carries the signature of the final plunge. The invisible becomes measurable without relying on light, and that is a conceptual shift. It suggests that horizons are not merely theoretical boundaries, but participants in a measurable process. The data do not show a picture of a horizon, yet they reveal its consequences with precision. Neutron star mergers add a different kind of meaning, because they connect extreme physics to familiar matter. They show that catastrophe is also creation, because heavy elements are forged in violence and then dispersed into galaxies. They link the fate of compact objects to the composition of planets and bodies, including the trace elements in biology and technology. They suggest that the chemical prerequisites for life may depend on rare, dramatic events scattered through galactic history. If such mergers were less frequent, would rocky planets be poorer in heavy elements, and would civilizations build different tools? The question is speculative, but it highlights how cosmic rates can shape local possibilities. The chapter's core facts converge into a new epistemology, where precision replaces proximity. We can measure distortions smaller than an atom's width across kilometers, and use them to reconstruct collisions across billions of light years. We can test relativity where it is most stressed, and we can trace the origin of precious elements to cosmic wreckage. We can combine messengers to locate events, measure expansion, and probe particle physics in extreme environments. The achievement is not only technological, it is conceptual, because it treats spacetime as an observable. In that sense, gravitational wave astronomy is a new way of doing astronomy, not merely a new instrument. Yet the most provocative implication points backward, not outward, and it points toward the boundary of our cosmic memory. If gravitational waves can carry information from before the CMB, then the earliest universe might be accessible in principle, even if the path is difficult. That would push our origin story closer to the beginning, toward inflation, quantum fluctuations, and the initial conditions that seeded all later structure. It would also reopen the question of whether our observable universe is one region among many, shaped by processes we have not yet fully tested. Listening in the end is also a way of asking where the first notes came from. We have followed light back to the CMB, the oldest photons we can directly see, and we have watched them arrive like embers from a long-quenched fire. On screen, the sky becomes a mottled oval map, hotter and cooler patches only tens of microkelvin apart, yet carrying a record of everything that followed. Beyond that luminous surface, the universe was an opaque plasma, a churning mix of electrons, nuclei, and photons scattering constantly. In that era, Ordinary images fail because light could not travel freely, and the cosmos had no transparent window. Yet the central question remains: what exists beyond what we can see, and how can we test it with more than imagination? When we say beyond, we mean two things at once: earlier than the CMB in time, and farther than the horizon in space. Both limits are real, and both force physics to speak in indirect signatures rather than direct photographs. The early universe is not hidden by distance alone, it is hidden by state, because matter and radiation once behaved like a fog. Fact 28. Inflation proposes a brief epoch of exponential expansion in the early universe, when the scale factor grew nearly like an exponential function. In a tiny fraction of a second, space itself may have expanded by an enormous factor, perhaps by 10^26 or more in linear size. The claim is not that matter flew outward into pre-existing emptiness, but that the metric stretched everywhere at once. Distances between moving points increased even if nothing locally moved. Visually, the idea is almost unsettling. A tiny patch, smaller than an atom, swelling until it could contain everything we now call the observable universe. In animation, grid lines painted on space pull apart smoothly. No center, no edge, just uniform stretching. The expansion is driven by an energy component with negative pressure, so gravity becomes effectively repulsive on large scales. In plain terms, the vacuum-like energy makes space expand faster instead of slowing down. Inflation was invented to explain puzzles that look like coincidences in the hot Big Bang, and its history is part of its appeal. In the late 1970s and early 1980s, cosmologists were wrestling with why the universe looked so special in its initial conditions. Alan Gough's original proposal, soon refined by Andre Linde and others, reframed those coincidences as outcomes of dynamics. The point was not to decorate the Big Bang, but to make its starting conditions less precarious. One puzzle is the horizon problem, revealed by the CMB's near-uniform temperature across the sky. Regions far apart appear too similar, even though light could not have travelled between them in standard expansion since the Big Bang. In the usual picture, those regions were never in causal contact, so they could not have shared heat or information. Uniformity, then, looks like a coincidence written across the whole sky. Inflation changes the causal story by rearranging what was once in contact, and it does so without violating relativity. Before inflation, the patch that became our observable universe could have been small enough to equilibrate, sharing temperature and density through ordinary interactions. Inflation then stretched that once connected region far beyond the horizon, leaving uniformity as a fossil, an ancient memory of a time when everything we see was close enough to talk. A useful visual is the stretching rubber sheet analogy, but the real concept is the comoving horizon. During inflation, the comoving horizon shrinks, meaning scales can exit causal contact even as the universe expands. That reversal is the mathematical heart of the solution, and it is why inflation is more than a metaphor. It turns an apparent impossibility into a geometric bookkeeping change. Another puzzle is the flatness problem, which is really about geometry and stability in the Friedmann equations. Small deviations from critical density grow over time in a decelerating universe, so near flatness today implies astonishing fine-tuning long ago. In other words, if the universe were even slightly curved early on, it should look dramatically curved now. Yet observations show space is very close to flat, meaning total density is near the critical value. Inflation drives the density toward critical by rapidly diluting curvature terms, and it does so with brute efficiency. Exponential expansion makes any initial curvature look flatter, the way a small patch of a large sphere looks plainer when you zoom in. In the equations, the curvature contribution falls away relative to the energy driving inflation. Flatness becomes an outcome of dynamics, not a finely chosen initial condition. Inflation also addresses relic problems, like why we do not see heavy exotic leftovers predicted by high-energy physics. Grand unified theories suggest that early phase transitions could produce magnetic monopoles and other stable relics. If those relics were created abundantly, they should still be around in overwhelming numbers. Yet careful searchers do not find them, and the universe does not behave as if they dominate its mass. Rapid expansion would dilute such relics to negligible densities in our region, effectively sweeping the cosmic stage clean. That does not prove inflation happened, but it shows why the idea was compelling to theorists. It turns multiple early universe puzzles into one mechanism with testable consequences. It also links cosmology to particle physics, because the same fields that shape inflation might connect to symmetries at extreme energies. The most important consequence is not about smoothness, but about structure, because the universe is not perfectly uniform and it never was. Galaxies, clusters, and the cosmic web require initial seeds that gravity can amplify. Without seeds, gravity has nothing to grip, and a perfectly smooth universe would remain smooth forever. The sky's rich hierarchy, filaments, voids, and knots, demands an origin story for tiny differences. Inflation supplies those seeds by stretching quantum fluctuations to cosmic scales, turning microscopic uncertainty into macroscopic pattern. Quantum fields cannot be perfectly still, even in their lowest energy vacuum state, because the uncertainty principle forbids exact zero fluctuations. The vacuum is not nothing, it is a restless baseline with jitter in field values and energy density. In plain language, the fabric has unavoidable noise. During inflation, these microscopic fluctuations are pulled outward, faster than causal processes can erase them, and that timing is crucial. They cross outside the horizon, where local microphysics can no longer smooth them out. In that regime, the fluctuations effectively freeze in amplitude, becoming classical-looking perturbations with well-defined phases. Later, as inflation ends and expansion slows, the horizon grows and these modes re-enter, now as real density variations. This is the bridge from quantum randomness to the largest structures in the sky, and it is one of cosmology's most audacious claims. It says the pattern of galaxies began as fluctuations in quantum fields, magnified until they became the blueprint for gravity. Small differences in density become gravitational wells, where dark matter collects first, because it does not feel radiation pressure. Ordinary matter falls in later, after it decouples from photons, forming stars and galaxies along an invisible scaffold. On screen, the visualization can shift from a smooth, pale fog to a faintly speckled field, then to a web of filaments forming as time accelerates. Dark matter appears as a ghostly lattice, and baryonic gas streams into it like mist into valleys. The voids grow emptier while the knots grow denser, and the universe begins to look like a network rather than a uniform cloud. The beauty is not decorative, it is physics made visible. The CMB is where we see the imprint of those primordial seeds most cleanly, because it is a snapshot taken when the universe first became transparent. Its temperature anisotropies map variations in density and gravitational potential at last scattering. Photons climbing out of potential wells lose energy, while those falling in gain it, a gravitational redshift effect that subtly modulates the map. Acoustic peaks encode how baryons and photons oscillated in early plasma, while dark matter shaped the wells that set the rhythm. Those oscillations were real sound waves, though the sound was pressure waves in a plasma rather than air. Radiation pressure pushed matter outward, gravity pulled it back, and the competition produced standing waves at different scales. The result is a harmonic pattern in the CMB power spectrum, like a fingerprint with multiple ridges. When we measure those peaks precisely, we are effectively measuring the universe's composition and geometry at 380,000 years old. Inflation makes a specific statistical prediction for these patterns, and it is surprisingly crisp given the vast extrapolation in time. The primordial perturbations should be nearly scale invariant, meaning similar power across a wide range of sizes. They should also be close to Gaussian, meaning the fluctuations behave like a random field with a simple probability distribution. In plain terms, the map should look like structured noise, not like a pattern drawn by hand. Planck and earlier missions found a spectrum broadly consistent with these expectations, and the precision is itself a triumph. The tilt is slightly red, meaning a bit more power on large scales than small ones, which fits many slow-roll inflation models. The data also constrain departures from Gaussianity to be small, limiting exotic interactions in the inflationary era. That match is a major reason inflation is taken seriously, even without a single unique model. Yet inflation is not one theory, it is a family of models, and that diversity is both strength and weakness. Different inflaton potentials, fields, and couplings can produce similar broad predictions, especially at the level of the simplest observables. Some models involve one scalar field rolling down a smooth potential, while others involve multiple fields or non-canonical kinetic terms. The evidence supports an inflation-like phase, but it does not yet identify the exact mechanism. This is where the chapter's tension sharpens around testability. because a framework can be right in spirit while uncertain in detail. We have a powerful explanatory structure with real observational hooks, anchored in measurable spectra and correlations. We also have a frontier where many versions fit, and some consequences drift toward the unobservable. The scientific question becomes, what additional signatures would force the model space to collapse toward a specific story? One of the cleanest discriminators would be primordial gravitational waves, the tensor modes of inflation. Inflation generically produces tensor fluctuations, ripples in space-time itself, sourced by quantum fluctuations of the gravitational field. Their amplitude depends on the energy scale of inflation, linking the early universe to physics far beyond accelerators. If detected, they would tell us not just that inflation happened, but roughly how energetic it was. We do not expect to detect these waves as individual events like black hole mergers, because their wavelengths are enormous and their signal is diffuse. Instead, we look for a statistical background, a faint imprint spread across the sky. The most promising signature is in the polarization pattern of the CMB, where scattering at last scattering and during reionization imprints preferred directions. Polarization is a subtle tracer, but it carries information temperature alone cannot. CMB polarization can be decomposed into E modes and B modes, a mathematical separation based on symmetry. E modes are gradient-like patterns produced efficiently by scalar density perturbations, and they are already measured precisely. Primordial gravitational waves would add a distinctive B-mode pattern, a curling component not made efficiently by scalars. In visuals, E modes look like radial and tangential streaks, while B modes swirl like tiny vortices. A detection of primordial B modes at large angular scales would be strong evidence for inflationary tensor modes. Because few other mechanisms produce that specific correlation pattern, it would also pin down the inflationary energy scale and narrow the space of viable models. It would be a rare case where the earliest physics leaves a unique fingerprint, not easily mimicked by later astrophysics. The question is whether nature made that fingerprint large enough for us to read. But the search is difficult because the sky is messy, and the signal is tiny, often far below the level of foreground emission. Galactic dust emits polarized light that can mimic B modes, especially at the frequencies many experiments use. Synchrotron radiation from electrons spiraling in magnetic fields adds another polarized foreground, stronger at lower frequencies. The Milky Way, in other words, writes its own patterns over the cosmic script. Even if the foregrounds are modelled, lensing complicates the picture in a way that is both nuisance and opportunity. Gravitational lensing by large-scale structure subtly remaps the CMB, converting some E modes into B modes. That lensing B mode is a real cosmological signal, and it teaches us about the distribution of matter. Yet it is also a contaminant for primordial searches, because it fills in the same channel we want to keep clean. So experiments must map polarization across multiple frequencies and subtract foregrounds carefully, using the fact that dust and synchrotron have different spectral behavior. They also need delensing, using maps of matter distribution to remove the lensing contribution statistically. The work is as much about calibration and systematics as it is about raw sensitivity. A tiny misestimated beam shape or a small temperature to polarization leakage can masquerade as profound discovery. The history includes a cautionary lesson about premature claims, and it is now part of inflation's cultural memory. In 2014, BSEP2 reported a B-mode detection consistent with primordial waves, and the announcement electrified the field. Later analysis with Planck data showed much of the signal was polarized dust, not the early universe. The result was not a failure of curiosity, but a demonstration of how hard the measurement truly is. That episode did not kill the idea. It clarified the standards, and it improved the community's methods. It showed how easy it is for foregrounds to masquerade as fundamental physics, especially when the desired signal is near the noise floor. It also showed how science corrects itself, by combining datasets, revising priors, and tightening error budgets. In the long run, the correction strengthened confidence in the process, even as it delayed the prize. Even without a tensor detection, upper limits are valuable because they carve away once popular models. They constrain the tensor-to-scalar ratio, often written R, and therefore the inflationary energy scale. Many simple high-energy models are already disfavored, pushing theory toward lower-scale or more complex scenarios. Limits also encourage sharper predictions because a model that can explain anything risks explaining nothing. Inflation also makes predictions about non-Gaussianity and running of the spectral index, which are subtle but revealing. Significant non-Gaussianity would point to multifield dynamics, sharp features in the potential, or non-standard interactions. Running would indicate that the tilt changes with scale, hinting at departures from the simplest slow-roll behavior. So far, observations find perturbations close to Gaussian and running consistent with small values, again aligning with simple inflationary pictures. Yet there is a deeper open question about initial conditions and the start of inflation itself, and it is not merely philosophical. Inflation can make the universe appear insensitive to earlier details, but it may require special conditions to begin, such as a sufficiently smooth patch dominated by the right kind of energy. Some models claim inflation is generic, an attractor that begins easily. Others imply it is rare, and the debate remains active because it touches what we mean by explanation. This is where inflation touches the multiverse question, not as an add-on, but as a possible dynamical consequence. In many models, inflation is not a one-time event that ends everywhere, because quantum fluctuations can keep inflation going in some regions even as it ends in others. This process is called eternal inflation, and it turns the end of inflation into a patchy, probabilistic event. The universe becomes a mosaic of endings rather than a single global finale. Eternal inflation produces a patchwork of bubble universes, each bubble a region where inflation ended and a hot Big Bang began. Different bubbles could realize different low-energy physics depending on how fields settled into vacuum states after symmetry breaking. In visuals, you might see a dark inflating background with glowing bubbles nucleating and expanding, separated by still inflating space. The imagery is dramatic, but the claim is technical. Quantum fluctuations can make the inflating state self-reproducing. We must separate what is implied by some models from what is observed, because the temptation to blur them is strong. We observe one universe, one CMB sky, and one expansion history in our region. The multiverse is a hypothesis about what lies beyond our horizon, not a confirmed empirical fact. It may be a natural extrapolation of certain equations, but extrapolation is not the same as measurement. The difficulty is that other bubbles may be causally disconnected forever, and that is not a mere practical obstacle. If signals cannot cross the inflating regions between bubbles, direct observation is impossible in principle. That raises a hard methodological issue. How does science evaluate claims about unobservable domains without slipping into unfalsifiable storytelling? The boundary between physics and metaphysics is not a wall, but it is a line that must be patrolled. Some proposals search for indirect signatures, like bubble collision imprints on the CMB, where our bubble might have been struck early on. A collision might leave a circular feature, a temperature discontinuity, or an unusual anisotropy pattern with specific symmetry. Searches so far have not found compelling evidence, which constrains certain scenarios but does not close the door. The absence of evidence becomes a quantitative statement, limiting how violent or frequent such collisions could have been. The multiverse idea also intersects with fine-tuning and cosmic coincidences, which are already present in the way we talk about constants. Many physical parameters appear to sit in narrow ranges that allow complex chemistry and long-lived stars. If the electromagnetic force were different, atoms might not form stable structures, and chemistry could collapse into monotony. If nuclear binding changed slightly, carbon and oxygen production in stars could be drastically altered, reshaping the periodic table itself. The cosmological constant is a particularly sharp example, because it controls the late-time acceleration of expansion. If vacuum energy were much larger, accelerated expansion would prevent galaxies from forming by pulling matter apart before it could collapse. If it were much more negative, the universe could recollapse quickly, limiting time for complexity. Either way, the window for a structured cosmos seems narrow, and our universe sits inside it. These observations create tension between two explanatory styles, and the tension is productive rather than embarrassing. One style seeks a deeper law that fixes constants uniquely, making life-permitting values inevitable and derivable. Another style invokes selection effects, where many domains exist and observers arise only where conditions allow them. The second style can feel unsatisfying, yet it mirrors how we reason in other contexts, where observation is conditioned on existence. Anthropic reasoning is not a substitute for measurement, and it can be misused when it becomes a conversation stopper. Yet selection effects are real in science. and they matter whenever observation is filtered by survivability or detectability. The challenge is to keep the argument disciplined, tied to models that also make testable predictions in our domain. A multiverse that explains everything but predicts nothing is not a scientific victory. Inflation sits at this boundary between strong evidence and speculative extension, and that is why it feels emotionally charged. The evidence supports an early smoothing and seeding mechanism consistent with inflation-like dynamics written into the CMB and large-scale structure. The multiverse is a possible consequence of some inflationary models, but it is not required by all. It is also not directly observed, which means it must be treated as an open hypothesis, not a settled fact. This boundary is the chapter's emotional hinge, because it changes how beginning sounds in our minds. If inflation is right, the beginning was not a single fireball, but a phase of accelerated expansion, perhaps followed by reheating when inflation ended. In that end phase, the energy driving inflation would convert into particles and radiation, filling space with a hot plasma. The universe's first structure may have been quantum noise, promoted to cosmic architecture by expansion. That idea reframes our place in the story of stardust and life, because it ties biography to statistics. The atoms in our bodies were forged in stars, but the pattern that gathered those stars began as fluctuations in a quantum field. Our existence may trace back to randomness that became law-like through statistics, because many random realizations share the same measurable distribution. It is a strange comfort. The details are accidental, but the pattern is predictable. It also reframes the central question about what lies beyond what we can see, and it forces us to be precise about ignorance. Beyond the horizon could be more of the same, shaped by the same physics and the same inflationary past. Or beyond the horizon could be a larger landscape, where our region is one realization among many, with constants set by local vacuum choices. Which picture is true, and what observation could ever tell us? Science advances by turning metaphysical-sounding questions into measurable ones, and inflation is a case study in that transformation. Inflation did that for horizon and flatness, by proposing a dynamical mechanism with observable relics in the CMB spectrum. The next step is to keep pushing the boundary of what can be tested, without pretending certainty where it is not earned. Awe is part of the motivation, but discipline is the method. Upcoming CMB polarization experiments, large-scale structure surveys, and gravitational wave observatories will tighten constraints and sharpen the story. Better delensing will clarify whether primordial B modes exist at detectable levels, and improved foreground modelling will reduce the Milky Way's interference. Measurements of spectral features and non-Gaussianity will further narrow the inflationary model space. Each new map is not just prettier, it is a more demanding interrogation of the early universe. A primordial gravitational wave background might also be probed at other frequencies, though each band corresponds to different physical scales and model assumptions. Pulsar timing arrays search for correlated timing shifts across the sky, sensitive to very low frequency waves with periods of years. Space-based interferometers will open a middle band, though primordial signals there are more model-dependent than the CMB case. The broader the frequency coverage, the more ways inflation can be constrained, or surprised. Each null result is still a map of what the early universe was not, and that negative knowledge matters. Each detection would be a direct connection between quantum theory and cosmic history, a rare bridge across scales. Either way, the early universe becomes less mythic and more constrained by data. The story does not lose wonder when it gains rigor. It gains weight. We end with the tension intact because it is honest and productive, and because the frontier is still moving. Inflation is a leading explanation with strong circumstantial support and specific tests, especially in the statistics of the CMB. The multiverse remains an open question, perched at the edge of inference and philosophy. It may be implied by some equations, but it is not yet anchored by observation. If inflation is right, the universe's beginning may be stranger than any myth, and stranger in a way that still obeys mathematics. It may also be stranger in a way that leaves measurable scars written into polarization patterns and the distribution of galaxies. The sky, in that sense, is not just scenery, it is an archive, and we are learning slowly how to read it. The central question narrows from horizons to hands, because what exists beyond what we can see also exists inside us as chemistry, with a cosmic origin. When we say cosmic, we do not mean metaphor, but a measurable chain of reactions that began long before Earth formed. The atoms in your body carry a history written in nuclear physics, and that history is readable if we know what to look for. The early universe made mostly hydrogen and helium, and almost nothing heavier, because it cooled too quickly for extended nuclear assembly. In the first minutes after the Big Bang, protons and neutrons combined into light nuclei, and then expansion diluted the density needed for further fusion. A trace of lithium formed as well, but the periodic table did not yet exist in any rich sense. Everything else required long-lived furnaces, repeated generations, and violent endings that could reset the chemistry of space. Starbirth begins in molecular clouds, cold enough for atoms to bond into molecules and for dust grains to survive without being vaporized. These clouds are thin by Earth standards, yet massive enough for gravity to matter over tens or hundreds of light years. In visible light, they look like absence, but in infrared and radio they glow with structure, filaments, knots, and dark lanes where starlight is swallowed. Gravity pulls inward, while gas pressure and turbulence push outward, and the contest is never perfectly balanced. Collapse starts where density rises, cooling stays efficient, and self-gravity wins locally over internal motions. Cooling is crucial, because hot gas resists compression, while cold gas yields and concentrates. In many regions, radiation from nearby stars also sculpts the edges, compressing some pockets while eroding others. As a region collapses, it fragments into clumps that will become many stars, not one monolithic object. The cloud does not fall as one piece, because small instabilities grow quickly, and because turbulence seeds uneven density from the start. Filaments feed hubs spawn clusters, and the resulting nursery can contain hundreds or thousands of newborn suns. In these crowded cradles, stars are not isolated points, but neighbours that compete for gas. A protostar forms when the central clump becomes opaque and heats up, trapping radiation that previously escaped. Infalling gas releases gravitational energy, and that heat becomes the first light even before fusion begins. The luminosity is powered by collapse, like a waterfall turning potential energy into motion and warmth. Around the protostar, an envelope of gas continues to rain inward, feeding the growing core. Rotation is never exactly zero, so angular momentum builds as the radius shrinks and spin speeds up. The result is a disk, because material can fall inward only by shedding momentum, and a flat structure is the easiest place to redistribute it. You can see the same principle in a spinning skater pulling in their arms, but here the scale is astronomical. The disk is not smooth either, because pressure waves and magnetic effects carve rings, gaps, and spirals. Magnetic fields and jets help remove angular momentum from the system, acting like invisible brake lines anchored in plasma. Outflows also clear cavities that let radiation escape, regulating how fast the star grows and how hot its surroundings become. Bipolar jets punch through the cloud, lighting up shock fronts where fast gas slams into slower material. These jets are signposts of formation, and in time-lapse they would look like lighthouses drilling into darkness. The disk is not a side effect, it is the staging ground for planets, and it is chemically active from the beginning. Dust grains stick, grow into pebbles, and begin the long path toward worlds through collisions that sometimes build and sometimes shatter. Ices condense in the colder outer regions, while closer in, heat drives reactions that alter minerals and organics. Even at this early stage, the distribution of carbon, oxygen, and nitrogen is being sorted into future atmospheres and oceans. A star becomes a true star when its core reaches fusion conditions, and gravitational collapse can no longer proceed unchecked. Temperature and pressure rise until protons can overcome repulsion and interact through the strong force, despite their like charges. Quantum tunneling makes this possible, allowing particles to slip through barriers that classical physics would forbid. In the Sun, this happens at roughly 15 million Kelvin, a number that is hard to imagine until you remember it is trapped inside a sphere of plasma. Fusion is a balancing act between gravity and pressure from hot plasma and radiation, a self-regulating engine rather than a bomb. If fusion lags, the core contracts and heats, and the reaction rate rises steeply with temperature. If fusion runs too hard, pressure expands the core and cools it, and the reaction rate falls back. This feedback makes main sequence stars stable for long spans, and it is why a star can shine steadily instead of flaring into a brief blaze. Hydrogen fusion turns 4 protons into helium, releasing energy through mass difference, because the final nucleus is slightly lighter than the ingredients. That missing mass becomes energy, and the conversion is described by Einstein's relation, a simple equation with enormous consequence. In the Sun's dominant chain, protons become deuterium, then helium-3, and finally helium-4, with neutrinos slipping away as near-ghostly byproducts. Those neutrinos pass through Earth by the trillions each second, reminders that the Sun's core is active right now. The energy emerges as photons after a long random walk outward, because light is repeatedly absorbed and re-emitted inside dense plasma. A photon born in the core does not travel straight to space, but staggers, scatters, and changes direction countless times. The journey can take tens of thousands of years, even though the final sprint from the Sun's surface to Earth takes 8 minutes. When sunlight warms your skin, it is ancient in a very literal way. The rate of fusion sets luminosity, and luminosity sets lifetime, tying a star's fate to its initial mass. A star is a fuel tank with a throttle, and mass controls the throttle by setting the pressure in the core. Add mass, and gravity squeezes harder, raising temperature and accelerating reactions. Remove mass, and the engine idles, conserving fuel over spans that dwarf human history. More massive stars burn hotter and brighter, so they exhaust fuel quickly, even though they start with more hydrogen. They live fast and die young, sometimes in only a few million years, which is brief on cosmic clocks. Their light is bluer because their surfaces are hotter, and their radiation sculpts their neighborhoods with fierce winds. In star-forming regions, these giants can both trigger new collapse and also tear clouds apart. Lower-mass stars sip their fuel and can shine for trillions of years because their cores are cooler and fusion proceeds more slowly. The universe is not old enough for the smallest red dwarfs to have died naturally, so none have yet reached their quiet endings. These stars are dimmer, redder, and far more numerous than Sun-like stars, making them a dominant population in the galaxy. Their longevity tempts habitability, but their magnetic tantrums complicate the promise. Stellar alchemy proceeds in stages as cores evolve, and each stage depends on what came before. When hydrogen in the core runs low, the balance breaks, and gravity forces a new chapter that the star cannot refuse. The core contracts and heats, while hydrogen fusion continues in a surrounding shell that grows more intense. The outer layers expand and cool, and the star becomes a giant swelling until it can engulf inner planets in extreme cases. In these expanded atmospheres, convection can dredge up material from deep layers, mixing new elements toward the surface. The star's light shifts toward red and orange, and its radius can become hundreds of times larger than before. If we could hover nearby, we would see a bloated sphere with a tenuous edge, shedding gas into space in slow winds. That mass loss matters, because it returns processed material to the galaxy, even without an explosion. Helium fusion begins when temperatures climb high enough for the triple alpha process, a reaction that requires extreme density and heat. 3 helium nuclei can combine, through a brief beryllium step, to make carbon, but the intermediate nucleus is unstable and usually falls apart. The fact that carbon forms efficiently is not obvious, and for a time it was a puzzle with existential weight. Without carbon, complex organic chemistry would be radically constrained, and the universe would feel chemically impoverished. Carbon is not guaranteed by simple arithmetic. It depends on nuclear resonance, a precise energy level that acts like a doorway. The Hoyle state makes carbon production efficient, shaping chemistry across the cosmos and enabling carbon-based molecules to become common. This idea emerged in the mid-20th century, when Fred Hoyle predicted the resonance before it was measured in the laboratory. It is a striking moment in science, where reasoning from the existence of life suggested a property of atomic nuclei. In more massive stars, carbon can fuse into heavier nuclei under higher temperatures, and the sequence becomes a layered architecture. Oxygen, neon, magnesium, silicon, and sulfur appear as the core grows denser, building shells like an onion with different burning zones. Each stage requires higher temperatures because heavier nuclei carry greater electric charge and resist close approach. The star's interior becomes a stratified furnace, with different elements dominating at different depths. These reactions release energy only up to a point, because fusion works by moving toward more tightly bound nuclei. Binding energy per nucleon rises toward iron, making lighter nuclei energetically eager to merge and release energy. This is why hydrogen fusion powers stars so effectively, and why helium fusion can follow when conditions intensify. But the curve flattens, and eventually the chemistry of energy turns against the star. iron marks an endpoint for energy-producing fusion in massive stars, because iron group nuclei sit near the peak of binding energy. Beyond iron, fusion consumes energy, so it cannot support the core against gravity, even if the star tries. At that stage, the core is like an engine that has run out of profitable reactions, forced to rely on pressure support alone. The star can still burn in shells outside the core, but the centre is now a trap. Once an iron core grows too massive, pressure support fails catastrophically, and the collapse begins in earnest. Electron degeneracy breaks as densities rise, electrons combine with protons, and the core becomes neutron-rich through inverse beta decay. This process also releases a flood of neutrinos, and it removes the electron pressure that had been propping the core up. In a fraction of a second, the core plunges inward at a significant fraction of the speed of light. The collapse is rapid, and it ends when nuclear forces and neutron degeneracy stiffen the core, halting the implosion like a compressed spring. The infalling outer core rebounds, launching a shock that struggles outward through layers that are still falling in. Early models found that the shock can stall, losing energy as it breaks apart heavy nuclei and fights gravity. The explosion is not automatic, and that difficulty is part of what makes supernova physics an active field. Neutrinos flood out, carrying away immense energy, and helping revive the shock through subtle interactions with matter. Most neutrinos escape freely, but a small fraction deposit energy behind the shock, adding the push needed to unbind the star's outer layers. The result is a supernova, an explosion that can briefly outshine an entire galaxy and seed space with new atoms. In the expanding debris, shock heating and rapid cooling create a changing laboratory of nuclear reactions. A supernova is destruction, but it is also dispersal, a mechanism for mixing a star's interior with the wider galaxy. Elements forged in the star are thrown into space, enriching the next generation of clouds that will someday collapse again. The blast wave plows into surrounding gas, compressing it and sometimes triggering new star formation in the aftermath. In images, we see delicate filaments and glowing shells, the visible handwriting of a star's final act. Supernovae also create new elements in the blast itself, because the explosion produces extreme temperatures and densities. In those moments, nuclear statistical equilibrium can briefly favour different compositions, and then freeze-out locks them in as the material expands. Some iron group elements are produced in these explosive conditions, adding to what was built during the star's life. The details depend on mass, rotation, and the star's earlier loss of material, making each supernova a slightly different recipe. One key route is neutron capture, where nuclei absorb neutrons and later beta decay, stepping upward in atomic number. Slow capture happens in some giant stars, where neutron flux is modest and nuclei have time to decay between captures. This is called the S process, and it tends to build elements along a path near stable isotopes. It is a patient kind of alchemy, operating over thousands of years in deep stellar layers. But the fastest capture needs extremes, environments where neutrons are so abundant that nuclei grab them faster than they can decay. The R process is rapid neutron capture in a neutron-saturated environment, and it creates very heavy, unstable isotopes in a rush. Those isotopes then decay back towards stability, producing characteristic abundance peaks that match what we observe in old stars. It is a violent shortcut to heavy elements, and it happens on timescales of seconds. This is how many of the heaviest elements are made, including gold, platinum, and uranium, which are rare but consequential. The periodic table's upper reaches are written by brief, violent conditions, not by slow, steady burning. When you hold a gold ring, you are holding matter that likely passed through an event of staggering intensity. It raises a quiet question. How many catastrophes are hidden inside ordinary objects? For decades, core collapse supernovae were the leading R process suspects, because they were known to be common and energetic. Some models struggled to provide enough neutrons in the right conditions, so the story widened to new sources without abandoning the old ones. The scientific arc here is historical as well as physical, because it shows how evidence reshapes confidence. We do not change the laws, but we refine the environments where those laws can do the work. Neutron star mergers provide a complementary R process site, and they are almost tailor-made for neutron richness. When two neutron stars collide, neutron-rich matter is ejected and decompresses, enabling rapid capture with extraordinary efficiency. The ejected material can be flung out in tidal tails and winds from the merger remnant, each with its own composition. As it expands, Radioactive decay heats it, powering a transient glow that changes colour over days. Gravitational waves reveal these mergers as real and frequent enough to matter, turning a theoretical channel into an observed one. Multi-messenger observations tied kilonova light to radioactive decay of freshly made heavy nuclei, linking physics across signals. The waveform tells us masses and dynamics, while the light curve hints at opacities shaped by lanthanides. It is astronomy with more than one sense, and it feels like a new way of knowing. The universe therefore has multiple factories with different schedules, and that timing shapes chemical availability. Supernovae enrich galaxies early and broadly, while mergers may add heavy elements in rarer, delayed bursts that arrive after binary systems spiral together. Chemical evolution becomes a history of rates and mixing, not a single uniform enrichment. A galaxy's element pattern records how often stars exploded, how often neutron stars merged, and how well gas stirred between events. This chemistry links back to earlier chapters about evidence beyond sight, because we rarely touch the material directly. Spectra are our ledger, because each element leaves a fingerprint in starlight and nebular glow through absorption and emission lines. When we split light into a rainbow, we find missing bands and bright spikes, each corresponding to quantum transitions. It is a coded message, and the code is the same in every corner of the universe. When we measure iron lines in old stars, we measure ancient supernovae because iron is a common product of massive stellar deaths. When we find europium and other R process traces, we infer rare neutron-rich events that must have occurred before the star formed. In the oldest halo stars, these signatures can be stark, suggesting early enrichment by only a few explosions. The stars become time capsules, preserving the chemical weather of the young galaxy. Fact 29. You're made of star stuff in a literal chemical sense, not as poetry, and the details are specific. The carbon in your cells was built by helium fusion in earlier stars, then released into space by winds or explosions. The oxygen you breathe and bind in water was forged in massive star cores and expelled by supernovae, then mixed into clouds that later formed the sun. The nitrogen in DNA was assembled through stellar burning and recycling, passing through multiple generations before it reached Earth. The calcium in your bones came from explosive burning and stellar interiors, and it had to survive the journey through interstellar space. The iron in your blood traces to massive stars and the supernovae that ended them, because iron is abundant in those final stages. Even the sodium and potassium that help your nerves fire are products of stellar nucleosynthesis, distributed by galactic mixing. Your body is a temporary arrangement of atoms that were once inside stars and that will someday return to space. Even trace elements matter for biology and technology, and their rarity can shape what is possible on a planet. Phosphorus for energy transfer, iodine for hormones, and zinc for enzymes all require prior stellar generations and specific nucleosynthetic pathways. Copper and molybdenum, vital for certain proteins, depend on environments that are not guaranteed everywhere. In this sense, life is not only about carbon, but about a supporting cast of elements that must be present in the right proportions. This makes the opening hook concrete, because it ties the cosmic to the intimate without changing the subject. If the universe can build the ingredients for life everywhere, the raw materials are not unique to Earth, and that is a profound constraint on our loneliness. Yet ingredients are not outcomes, and chemistry does not guarantee biology, even if the pantry is well stocked. The same processes that create carbon also create radiation, shocks, and sterilizing environments that can erase fragile beginnings. The tension becomes a question of probability across time and space, and it is sharpened by the universe's vast sample size. Is life a rare accident in a vast chemical sea, or a common outcome of rich chemistry given enough trials? If the same nucleosynthesis happens in billions of galaxies, does biology eventually become likely? Or does it remain improbable for reasons we have not yet measured? The question is not only philosophical, because it guides what we search for and where we search. Stars vary in mass, lifetime, and stability, and those differences shape habitability in practical ways. Short-lived massive stars enrich quickly, but they also end violently and disrupt nearby systems with intense ultraviolet light and supernova blasts. Long-lived smaller stars offer long windows, but their early activity can strip atmospheres through flares and strong stellar winds. The path from elements to ecosystems depends on stellar behavior as much as abundance, because a stable environment is part of the recipe. Galaxies also differ in how they mix metals and form new stars, and that diversity creates chemical neighborhoods. Some regions become metal-rich early, while others remain primitive, delaying rocky planet formation and limiting available materials. Even within one galaxy, timing matters, because enrichment is patchy and mixing is not instantaneous. Planets forming too early may lack heavy elements, while planets forming too late may face higher radiation backgrounds from accumulated stellar remnants. So the universe is both generous and selective, offering the periodic table widely, but distributing it unevenly. It produces the elements needed for complex chemistry, yet it tests them with harsh physics, radiation, impacts, and the volatility of young systems. This chapter also reframes meaning in a measurable way, because our bodies are not separate from cosmology. Our atoms are evidence of ancient stellar histories, and the evidence is embedded in ordinary matter. We can trace that history with isotopes and abundances, turning biology into a cosmic fossil record that complements rocks and genomes. Meteorites preserve early solar system chemistry, and stellar spectra reveal the broader galactic context that preceded it. The boundary between astronomy and life science becomes porous, because both depend on the same elemental inventory. When we ask where life could arise, we're also asking where the right nucleosynthetic past has occurred. The stakes rise because element creation is also a constraint on where life can arise, not merely a poetic origin story. Without carbon and oxygen, there is no familiar biochemistry, and without metals, there are few rocky worlds with solid surfaces. At the same time, the universe has had billions of years to iterate, and each generation of stars changes the next. Later planets can be chemically richer than earlier ones, and that enrichment may widen the menu of possible geologies and atmospheres. The central question returns with sharper edges, because chemistry sets the stage but does not write the play. Beyond what we can see may be countless enriched systems, or vast regions still chemically young, waiting for time to do its work. We cannot visit most of them, but we can infer their ingredients from light and from cosmic history, using the same indirect logic that reveals invisible mass. The same method that helped expose dark matter also reveals our own origins, because both are traced through their effects. For most of history, planets around other stars were speculation with no data attached, a philosophical guess dressed in astronomical language. Ancient thinkers argued about other worlds, yet telescopes could not separate a planet's faint glow from a star's glare. Even into the 20th century, the idea remained plausible but untested, more like a map drawn from rumour than measurement. In one generation, that changed into catalogues, statistics, and a new kind of cosmic map, built from repeated observations rather than hopeful analogy. The shift came from better detectors, stable spectrographs, and space telescopes that could stare without atmospheric flicker. Suddenly, the night sky became not just a backdrop of stars, but a population study of planetary systems. Exoplanets are found indirectly, because the planets are dim and their stars are blinding, like fireflies lost beside stadium lights. We do not start with pictures, and we rarely get the satisfaction of a resolved disk. We start with tiny, repeatable effects, signals that physics cannot fake, and that careful statistics can confirm. The transit method watches a star's brightness for periodic dips caused by a planet crossing, a miniature eclipse that repeats with clockwork precision. The dip might be less than 1% or only a few dozen parts per million for an Earth-sized world. From the depth of the dip, we infer the planet's radius, relative to the star's size because a larger disk blocks more light. From the timing of repeated transits, we infer the orbital period and distance, using Kepler's laws and the star's mass estimate. The interval between dips becomes an orbital metronome, and the period points to how much starlight the planet receives. From the shape of the dip, we infer impact parameter and hints of orbital inclination, because a grazing transit looks different from a central one. Transits also let us measure the planet's climate geometry, because starlight is blocked in a predictable pattern across the stellar face. Subtle asymmetries can hint at star spots, rings, or even a planet crossing bright stellar regions. With multiple wavelengths, the dip changes slightly when an atmosphere absorbs specific colours, turning a simple light curve into a spectrum of possibilities. That technique is transmission spectroscopy, and it turns a silhouette into a chemical probe, using the atmosphere as a thin filter. During transit, a small fraction of starlight skims through the planet's limb, where gases imprint absorption features, It can reveal water vapor, sodium, carbon-bearing molecules, and hazes that flatten spectral features, because aerosols scatter light and hide deeper layers. The physics is straightforward but unforgiving. The signal scales with the atmospheric scale height, which depends on temperature, gravity, and molecular weight. A hot, puffy hydrogen atmosphere leaves a strong imprint, while a cold, heavy atmosphere can be nearly invisible. This is why some worlds look chemically blank, not because nothing is there, but because clouds and high gravity can mute the signature. Radial velocity uses a different effect, because planets tug their stars gravitationally, and the star responds with a tiny reflex motion. The star's spectrum shifts back and forth from Doppler motion, revealing a periodic wobble that matches the planet's orbit. The best instruments measure shifts of meters per second, and the next generation pushes towards centimeters per second, precision that borders on the absurd. From the wobble amplitude we infer a minimum mass, because inclination is usually unknown, and the motion we see is only along our line of sight. Combined with transits, inclination becomes known, and the true mass emerges, letting us weigh the planet rather than just bracket it. When mass and radius are both measured, the planet stops being a dot in a catalogue and becomes a physical object. Mass and radius together give density, which separates rocky worlds from gas-rich ones with a single calculation. A small radius with high density implies iron and rock, perhaps with a metallic core and silicate mantle. A larger radius with low density implies thick volatiles, like hydrogen and helium, or deep layers of water and ices under crushing pressure. Direct imaging is the hardest approach, because it tries to see the planet's own light while suppressing the star. It works best for young hot planets far from their stars, where contrast and separation are kinder, and the planet still glows from formation heat. Coronagraphs and starshades act like artificial eclipses, blocking the star so the surrounding darkness can reveal a faint companion. Direct images can yield spectra without waiting for transits, revealing clouds, temperatures, and molecules in the planet's emitted or reflected light. They also show orbital motion over years, turning dots into dynamical systems with measured trajectories. In time-lapse, the planet creeps against the stellar background, and the geometry of the system becomes real rather than inferred. Microlensing uses gravity itself as a detector when a foreground star briefly magnifies a background star through space-time curvature. A planet adds a short extra blip, revealing mass ratio and projected separation, often for worlds that would otherwise be unreachable. The light curve rises and falls like a smooth hill, and the planetary signal appears as a sharp kink, an instant of revelation. Microlensing is powerful for cold planets far from their stars, even in distant parts of the galaxy where other methods struggle. It is also fleeting, because the alignment happens once and does not repeat, leaving no easy second chance. The event is a cosmic coincidence, and astronomers must be ready when the lensing geometry briefly lines up. Each method has biases that shape what we think is common, and those biases are not minor details. Transits prefer close-in orbits, because the chance of alignment drops with distance. Radial velocity prefers massive planets, because they tug harder and produce larger Doppler shifts. Imaging prefers wide, young giants, while microlensing samples different neighborhoods and different stellar populations. When we correct for those biases, the conclusion is blunt and unsettling. Planets are not rare, and they are not exotic exceptions. In the Milky Way, stars typically have planets, and many have multiple worlds arranged in compact, resonant architectures. The solar system becomes one example among many, not the template we assumed. This statistical flood reframes the central question about what exists beyond what we can see, because abundance changes the logic of possibility. If stardust can assemble into chemistry and planets everywhere, then the universe has many stages for life. The question shifts from can it happen to how often does it happen and under what constraints. But habitability is not a label we can stamp from distance alone, and it is not a single number in a database. It is a balance of physics, chemistry, and time, and it can fail in many quiet ways. A planet can look promising in orbit and size, yet be sterile because of its atmosphere, its history, or its internal evolution. The first requirement is liquid water, not because water is magical, but because it is an efficient solvent with unusual properties. Water's polarity helps it dissolve salts and transport ions, and its heat capacity buffers temperature swings. It supports complex reactions, enables membranes and gradients, and stays liquid across a broad temperature range that is forgiving by chemical standards. Water also depends on pressure, so a planet's atmosphere matters as much as its distance from the star. Too little pressure and water boils away, even in moderate temperatures, because the phase diagram forbids stable liquid. Too much pressure and water can become exotic high-pressure ice, where the ice is denser than liquid and behaves like a different mineral layer. Energy is the second requirement, because life needs a gradient to exploit, a difference that can be tapped and maintained. Sunlight is one option, providing photons that can drive photosynthesis and surface chemistry. Chemical energy from rocks and fluids is another, where redox reactions release usable energy in darkness. Tidal heating can substitute for starlight, kneading interiors and powering hidden oceans. Atmospheric stability is a third requirement, because climates drift without feedback and can cross irreversible thresholds. Greenhouse gases can warm a world, but runaway greenhouse can sterilize it by evaporating oceans and thickening the air. Too little greenhouse can freeze oceans globally, increasing albedo and locking the planet into a bright, cold state. A magnetic field can help by deflecting charged particles and reducing atmospheric erosion, especially for planets close to active stars. It is not a guarantee because chemistry and gravity still matter, but it can slow the stripping of upper atmospheres. A dynamo requires a conductive interior and motion, often a molten core, so magnetism is tied to deep planetary evolution. Stellar activity sets the background hazard, especially for small, cool red dwarfs, which dominate the galaxy's census. These stars are common and long-lived, but they flare often, blasting UV particles at close-in planets in their habitable zones. The habitable zone moves inward for dim stars, and that proximity increases exposure to magnetic storms. Flares can erode atmospheres, alter chemistry, and bathe surfaces in radiation, reshaping molecules faster than biology can adapt. Yet they also provide energy that could drive prebiotic chemistry, creating reactive species and complex organics in the upper atmosphere. The same violence can both hinder and help, an uncomfortable duality that forces careful modelling. Habitability also depends on geology, because planets are not static balls of rock, and their interiors do not stay quiet. Volcanism can replenish atmospheres with carbon dioxide, water vapour and sulfur compounds, rebuilding what escape removes. Plate tectonics may recycle carbon and stabilize climate over long times, but it may not be universal, and stagnant lid worlds may regulate themselves differently. We therefore search for atmospheres, because atmospheres are where biology could leave a remote signature that crosses interstellar distance. A planet's air is a global sample, mixed by winds and shaped by chemistry, sunlight and surface exchange. Even if life is localized, gases can spread, accumulate and become detectable as a planet-wide fingerprint. Biosignatures are not single molecules that shout life with certainty, because nature can imitate life's chemistry. They are patterns, especially chemical disequilibrium that is hard to maintain without continuous sources. The question is not only what is present, but what combination persists despite reactions that should erase it. Oxygen is a famous candidate because it is reactive and would normally disappear into rocks and reduced minerals. On Earth, abundant oxygen is tied to photosynthesis and long-term burial of carbon, a planetary-scale bookkeeping that leaves O2 behind. It also took time, hundreds of millions of years, for oxygen to rise and stabilize, reminding us that biosignatures can be delayed. Methane is another candidate because it is also reactive in oxygen-rich air, and sunlight breaks it down on relatively short timescales. On Earth, methane and oxygen together indicate a continuous replenishment that biology supplies at large scale, because the two gases should destroy each other. This tension between production and destruction is the clue, not the romance of any single molecule. The key is the combination, not the isolated detection, because isolated detections invite misinterpretation. Oxygen alone can be produced abiotically by photodissociation of water and escape of hydrogen, especially around active stars with strong UV. Methane alone can be produced by geology, including serpentinization in hydrothermal systems, where water reacts with ultramafic rock to release hydrogen. Even carbon dioxide and water can be present on dead worlds, because they are common products of planetary formation and outgassing. A spectrum can look Earth-like in a superficial way, while hiding a lifeless surface beneath clouds or haze. The discipline is to treat every promising line as a hypothesis, then try to break it with alternative explanations. False positives are the discipline that keeps awe from turning into wishful thinking, and they are central to the search. We must model the star's spectrum, the planet's temperature, and the chemistry that sunlight drives, because photochemistry can build surprising molecules. We also must understand surfaces, oceans, and escape processes, because a planet is a coupled system, not an atmosphere in isolation. Transmission spectroscopy during transits is one of our best tools, because starlight filters through the limb of the atmosphere in a long slant path. Absorption lines and slopes reveal molecules, clouds, and scattering particles, and the wavelength dependence can distinguish Rayleigh scattering from larger aerosols. The atmosphere becomes a thin ring of information, and we read it one transit at a time. Emission spectroscopy and phase curves add another angle, measuring a planet's own thermal glow as it orbits and changes aspect. They can reveal day-night temperature contrasts and the efficiency of heat transport, which depends on winds and radiative timescales. A phase curve is like watching a rotating ember, brightening and dimming as different hemispheres turn toward us. Future telescopes aim to measure smaller planets and thinner atmospheres, where signals are far weaker and noise becomes an adversary. The challenge is not only sensitivity, though photon counts matter. It is separating planetary features from stellar variability and instrument systematics, because star spots and detector drift can masquerade as atmospheric lines. As we refine these tools, the worlds themselves become stranger than early science fiction, because nature explores parameter space without nostalgia. Exoplanets are not just other Earths, and they are not just scaled versions of our neighbours. They are other physics regimes, where gravity, temperature, and composition combine into unfamiliar outcomes. Super-Earths are one example, planets larger than Earth but smaller than Neptune, and they appear to be common. Some may be scaled-up rocky worlds with deep mantles and higher surface gravity. Others may be mini-Neptunes with thick hydrogen envelopes, where the surface is a high-pressure boundary buried under thousands of kilometers of atmosphere. A small change in mass can change everything, because gravity reshapes atmospheres and interiors in nonlinear ways. Higher gravity can hold onto light gases, preventing escape that would strip smaller worlds. It can also raise pressure enough to alter mineral phases deep below, changing convection and the likelihood of a long-lived magnetic dynamo. Some close-in planets are lava worlds, where dayside temperatures melt rock into magma oceans that glow in infrared. Their atmospheres may be made of vaporized minerals, with sodium, silicon monoxide, and metal oxides drifting above molten ground. Along the terminator, rock vapor can condense, creating a cycle that resembles weather, except the water is stone. On tidally locked planets, one hemisphere faces the star permanently, creating permanent day and night and a stark energy imbalance. That geometry can drive extreme winds as air races to redistribute heat, rising on the day side and sinking on the night side. The terminator can become a ring of turbulence, where jet streams shear and clouds form in perpetual twilight. Some hot Jupiters show super-rotating winds, where jet streams circle the planet faster than the planet rotates, driven by intense stellar heating. Heat is pushed eastward, shifting the hottest point away from the substellar spot, and phase curves reveal that offset as a measurable asymmetry. In these atmospheres, dynamics is not a detail, it is the climate. Physics allows bizarre precipitation when temperatures and chemistry change with altitude, and condensation follows unfamiliar phase boundaries. In some atmospheres, silicate clouds can form, and condensed particles can fall like glassy rain, sparkling briefly before vaporizing deeper down. At higher temperatures, iron can condense and rain out, because metals can become atmospheric constituents under the right conditions. These are not metaphors, they are phase diagrams applied to alien skies, the same thermodynamics taught in classrooms but executed at extremes. Gas giants can host storms on scales that dwarf Earth's, because their atmospheres are deep and their rotation is fast. Without a solid surface, storms can persist and feed on internal heat, tapping energy stored from formation and slow contraction. Lightning can be colossal, because convection, particle collisions and charge separation can occur in thick clouds with high velocities. Radio observations and optical flashes suggest powerful discharges in giant planet atmospheres, and models predict lightning that could outshine terrestrial storms by orders of magnitude. Each flash briefly illuminates cloud tops, revealing structure like a camera strobe in a hurricane. These extremes matter for life because they test the limits of stability and chemistry, and they show how varied planet can be. They also expand our imagination of what counts as a habitable environment, because habitability is not limited to calm, Earth-like weather. If life is adaptable, it may exploit niches we would not think to label as friendly. We tend to picture life on surfaces under sunlight, because that is our example and our bias. Yet our own solar system suggests a different lesson, one written in ice and darkness. Some of the most promising habitats may be hidden, protected from radiation by kilometers of frozen shell. Ocean worlds with ice shells show how liquid water can exist far from the traditional habitable zone, where sunlight is weak. Europa and Enceladus are cold at the surface, yet likely warm inside, and their fractured ice hints at motion beneath. Plumes and surface features suggest exchange between ocean and crust, an important detail because chemistry needs contact. Their heat source is tidal heating, produced when gravity flexes a moon's interior during an eccentric orbit around a giant planet. Friction converts mechanical stress into heat, keeping water liquid beneath ice, and the heating can be sustained by orbital resonances. The system becomes a machine. Gravity supplies the forcing and the interior dissipates it as warmth. Hydrothermal vents on the seafloor can provide chemical energy, mixing reduced minerals with oxidants and creating steep redox gradients. On Earth, such environments host ecosystems independent of sunlight, where microbes feed on chemical disequilibrium rather than photons. The vents also concentrate minerals and surfaces, offering catalytic sites that may matter for the origin of life. These moons become analogues for exoplanets and exomoons, because the mechanism is general and does not depend on our particular sun. If a planet has a thick ice shell and tidal flexing, it can host a dark ocean, even if the surface is hostile. That possibility widens the search beyond the narrow idea of Earth-like surfaces, and it forces us to consider life that leaves only subtle atmospheric traces. It also complicates detection, because subsurface life may not alter an atmosphere strongly, and the ocean may be sealed away. A world could be alive and still look quiet from afar, its biosphere hidden under ice like a whisper behind a wall. This is one reason the search must remain probabilistic, not absolute. We now arrive at the chapter's culminating claim, the fact that sounds simple, but changes strategy. Fact 30. The Goldilocks zone is not a guarantee of life. The habitable zone only describes where stellar heating could allow surface liquid water, given a suitable atmosphere and the right greenhouse balance. It says nothing about whether a planet has water, continents, or long-term climate regulation, and it cannot encode a planet's formation history. It is a necessary condition in some cases, but it is never sufficient. A world can sit in the zone and still be sterile, because it formed dry or lost its water early through escape and photochemistry. It can be baked by runaway greenhouse, where water vapor amplifies heating until oceans vanish. Or it can be frozen by weak greenhouse and high albedo, reflecting starlight back to space until ice dominates. A world can also be habitable outside the zone, powered by tides, radioactivity, or thick insulating atmospheres that trap internal heat. Habitability is a system property, not a single orbital distance, and systems have many moving parts. The planet, the star, and the passage of time form a coupled story, and the ending is not predetermined. Geology matters because it shapes recycling of carbon and nutrients, and it controls volcanic outgassing that can rebuild atmospheres. Chemistry matters because oceans can become too acidic, too salty, or too reducing for familiar biology, even if liquid water is present. Time matters because life may require long, stable windows, and because biosignatures can take billions of years to accumulate. Chance matters because impacts, orbital chaos, and stellar evolution can reset the clock, erasing progress or redirecting it. A single giant impact can strip an atmosphere, tilt an axis, or deliver volatiles that change everything. A slow brightening star can move the habitable zone outward, turning yesterday's paradise into tomorrow's desert. So the era of exoplanets is also the era of humility, because the sample size is huge but the evidence is thin. We can count worlds easily, and we can classify them by size and orbit with growing confidence. We cannot yet read their histories, and without history, habitability remains an informed guess. Still, the numbers press on the mind, and they do not let us retreat into comfortable uniqueness. If there are billions of potentially habitable worlds in one galaxy, then across the observable universe there are staggering opportunities for life. The night sky becomes not just distant light, but a statistical argument that something should have happened elsewhere. That abundance creates a tension that is no longer philosophical because it collides with observation. If life and intelligence are common, we might expect signals, artifacts, or at least unambiguous atmospheric fingerprints that stand out from chemistry. Instead, we face a quiet sky where hints exist but certainty does not. Radio searchers have not found a clear, repeated technological beacon, despite decades of scanning and improving sensitivity. No probe has announced itself, and no unmistakable city-like glow has been confirmed on the night side of a distant planet. The silence is not proof of absence, but it is data, an emptiness we must interpret carefully. This is where the Fermi paradox enters, not as a punchline, but as a cliffhanger built from arithmetic and time. Where is everybody, if the galaxy is old and planets are common, and if even a small fraction of civilizations expand or transmit? The paradox is the gap between what seems plausible and what we actually see. Possible answers branch into uncomfortable categories, and none can be dismissed with a slogan. Maybe life is rare, because the origin of life is a hard step, requiring conditions we do not understand. Maybe complex life is rare, because multicellularity is fragile and depends on environmental stability and energy availability. Maybe intelligence is common but short-lived, because technology carries self-destruction risks and ecological constraints. Maybe civilizations are quiet by choice, or their communication methods are invisible to our searches, using channels we have barely imagined. Or maybe the timescales rarely overlap, and we are separated not by distance alone but by history. Maybe we are early, arriving before the galaxy fills with long-lived societies, and the silence is simply the calm before emergence. Maybe we are in a region that is unusually empty, shaped by history we have not measured, where sterilizing events were more common. Or maybe we're missing the signal because we are listening incorrectly, for too short a time, on too narrow a band. The silence could be real, or it could be a limitation of our instruments, an observational horizon disguised as loneliness. How many years of listening would count as long enough in a galaxy billions of years old? How many frequencies, modulation schemes, or non-radio technologies would we need to consider before we claim the sky is truly quiet? The paradox sharpens the central question again, because it forces us to confront what we can infer from absence and what we cannot. Beyond what we can see may be crowded with life, yet still unreachable by light and time, or simply unrecognizable to our methods. The universe may be full of stories that never intersect, like ships passing in a fog too thick for signals. We are stardust asking whether stardust elsewhere ever learns to ask back, and that is a strange, intimate thought. The universe has built atoms, stars, and planets with consistent laws, and it repeats those laws across unimaginable distances. The next step is whether it builds minds often, or only once, and whether minds tend to endure. The climax is not an answer, but a choice of method and a commitment to patience. We keep expanding our detectors, refining our models, and learning to read faint spectra as evidence rather than wish. Each new telescope is a new way of asking the same question, with better grammar and fewer assumptions. Transition. To end the journey, we confront the biggest question of all: what the universe's silence and grandeur mean for our future and our place in the cosmos. We end with a contradiction. Planets are common, chemistry is universal, yet evidence of others is absent. The Fermi paradox, sharpened in the mid-20th century, asks why high probabilities meet a quiet sky. Solutions cluster around a few sober categories. Life may be rare because abiogenesis is a narrow chemical bottleneck, intelligence rarer because evolution favors survival over reflection. Civilizations may be brief on cosmic clocks, extinguished by self-limits or by astrophysical hazards that reset the board. Interstellar travel may be brutally expensive in energy and time, while advanced technology may be quiet by design, low leakage, encrypted, or simply uninterested in broadcasting. Or our searches may be narrow, tuned to familiar bands and short campaigns, missing signals that are intermittent, faint, or alien in form. Human lifetimes are tiny windows, so technosignatures become cosmic archaeology, fragments of heat, light, or engineered chemistry left behind. Transition. We build new tools to widen the window. Next, CMB maps test inflation, dark matter, and dark energy's equation of state, tracing subtle polarization patterns across the oldest light. Gravitational wave observatories probe early epochs and unseen mergers, turning space-time itself into a detector. Exoplanet spectra hunt, disequilibrium gases and false positives, weighing biology against geology in thin, backlit air. Some horizons stay unseeable, yet inference remains rigorous, anchored by statistics and cross-checks. The arc holds. First light to cosmic web, to elements, to worlds. Beyond sight lies information, waiting, not for belief but for measurement. We followed light backward through time, from nearby moons and suns to deep fields, until the trail met the cosmic microwave background's ancient fire. Along the way, spectra named the elements, redshift measured expansion, and the cosmic web revealed an unseen architecture where dark matter shapes galaxies. Then the story widened again, as dark energy drove a runaway future. Black holes tested the limits of space-time, and gravitational waves let us hear collisions light cannot carry. We watched inflation turn quantum jitter into the seeds of structure. We traced stellar alchemy into the atoms of our bones, and we counted exoplanets until other worlds became a statistical certainty. Finally, the quiet sky forced the Fermi paradox into focus, reminding us that abundance does not guarantee company, and silence is also data. Taken together, these facts don't shrink humanity, they sharpen the method, because the universe is not only vast, it is legible in patterns we can test. Even our biggest unknowns now have edges, drawn by lensing maps, supernova distances, CMB polarization, and the faint chirps of merging stars. Beyond our vision, we found not emptiness, but structure, scaffolding without light, horizons that limit messages, and histories written into relic radiation and elemental fingerprints. And in every chapter the same theme returned, that the cosmos keeps its secrets not by hiding forever, but by demanding better questions and better instruments. So what exists beyond what we can see, and how do these extremes reshape meaning, origins, and life out there? Beyond the observable horizon may lie more of the same physics, or different initial conditions entirely. But our answer is this: we infer the unseen by how it bends, cools, clusters, and expands the part we can measure. The strangest facts did not end the search for meaning, they reframed it, because meaning grows where curiosity meets evidence, and where stardust learns to take notes. If the universe can assemble cosmic ash into minds that wonder, then the next step is not guessing what's beyond, but building the tools to listen harder and look longer. In the end, the greatest mystery is not that the universe is stranger than we imagined, it is that it is strange in ways we can quantify. The horizon may be a boundary for light, but it is not a boundary for understanding, because every new measurement turns wonder into knowledge, and knowledge into a deeper kind of awe. Stay with the questions, support the science that makes them testable, and keep watching the sky as if it can answer back.